So we'll see some of the search algorithms which you have already studied, and we'll see some of the new type of search algorithm which is there in artificial intelligence. So this is the agenda for this 2 hour lecture. We'll start with what are the important parameters you need to consider for a search. We'll also see how to carry out uh, a particular search or how to find a particular solution. And we'll also see that what are the components you need to consider whenever you are searching for a particular element. Then we'll see some of the search strategies. The search strategies may be based on, you can say, whether you have sufficient information to carry out the search or you have limited information to carry out the search. So based upon that, the search strategies are divided, or search algorithms are divided into uninformed or blind search. Another type of algorithm is called as informed search. So as you can see the name, uninformed, because there is no information with you while you are searching for a particular element. Like suppose you visited a particular, you want to visit a particular city. Once you reach to that particular city, you don't know where to stay. So you have not done any kind of background work to stay in that particular city. If you take this example, this is completely uninformed because you don't know, based upon your location or based upon the price, you can choose any hotel. But when you go for informed search, you have some kind of information available with you to choose a particular element or to explore a particular element. So these are the basic categorization of different search algorithms. We'll see number of algorithms under uninformed search and set of algorithms under the informed search. Then there is another interesting area that is called as game. Like one of the game I already told you in my first lecture about TikTok toy. One game may be chess, another game may be backgammon game. There are a lot of games are there. So if you can see in that particular game, you have to find what kind of search strategies you can apply there. Like if you talk about a particular environment, we can say whether the environment is fully explorable or it is partially explorable or it is not explorable at all. Like that you can make a categorization. So we'll see one game tree for TikTok toy. We'll see some of the evaluation functions. Through that evaluation function, you can uh, see the performance of a particular game, see the performance of your opponent, see the performance of a particular agent. That we'll see. And we will end up this lecture by Minimax search, which is a very popular search in artificial intelligence. So let us start the introduction part. I'll show you a very simple example in each and every case so that you will feel comfortable to understand what are the different search strategies available in artificial intelligence. So here, let us see how to search for a particular solution. So basically, I am going to take the map of Romania. Okay, and whatever discussion we'll make in today's lecture, these all are associated with the cities that are part of the Romania, various cities of Romania. And you have to apply the search strategy to move from one city to another city. So our starting city is Arad. We represent it by A when you represent by it in the form of a graph. And our objective is to reach a city B. With the alphabet B, there is a city in Romania. Our objective is to move from city A to city B. But the main challenge of this particular problem is that there is no direct path between A and B. In the sense is that the city A and city B are not directly connected to each other. That means Like you can say New Delhi and Hyderabad. So in between New Delhi and Hyderabad, there are number of intermediate cities. If you consider each and every city as a node, if you represent in the form of a graph, in that graph you will see New Delhi is not directly connected to the Hyderabad, right? So what I will going to do, first we are in the initial state. The initial state is our Arath. Then I am going to expand my initial state. So when I expand my initial state Arath, I found that there are three different cities that are connected to Arath. And these cities are called as S. I'm telling only the first alphabet to easily find the solutions. Second city that is connected to A is T. Third city that is connected to A is Z. Okay, like if I ask you, you go to your hometown, you first you see your hometown. What are the nearest cities to your hometown? Multiple cities may be near to you as for your hometown. So you have to choose which city is more nearer to you. Like here, I am interested to know the distance between A to S, the distance between A to T, the distance between A to Z. Okay, because if you want to find a particular search and you know your destination is not directly connected to your source, so you have to go through some intermediate cities, and there you have to explore one more time again. You reach to another city, again explore. This process is a iterative process, and our objective is to reach to the city number B. Like here you can see when you expand A, you got S, T, and Z. But what is your destination? Your destination is B. So neither B is equal to X or B is equal to T or B is equal to Z. So your search is not ending here. What you have to choose? You have to choose one of the city, either S or T or Z as your neighbor city, and again expand that particular city. For example, I found that the distance between Arath to uh, S, okay, is closer in comparison to A to T, A to Z. That's why I have selected S is my neighbor city of Arath. Right? If the cost is minimum for T, you choose T. If the cost is minimum for Z, you choose Z. Right? So once you found that S is having least distance from Arath, then what you will do? You have to expand S. Right? So if I expand S, I'm getting more cities that are connected to S. The name of the cities that are connected to S is F, O, and R. These three cities are connected to S. But one more interesting thing you can see here is Arad is connected to S or A is connected to S. S is also connected to A. So while you are exploring the neighbor city, you can see Arad is the again coming in your search query. That means the same city where you came from, the same city is again coming when you explore that particular city. And in case if the distance between A to S or S to A, especially S to A, if it is least in comparison to S to F, S to O, S to R, then you will find that there is a low. Right? You came from A to S, again you apply search query, then let's say again you are finding A. So if this is least one, this path is least one, then there is a low. That's why this is very much challenging while you are exploring the neighbor city of S. A should not come. Even if A is coming, you have to exclude it. That's why when you go for search strategy, you will come to know we prepare two lists. One is called as open list, another is called as closed list. As the name suggests, open list means the cities which are not explored, and closed means the cities that are already explored. In order to avoid this loop problem, we maintain two different lists. Okay, we'll see more about this while we are discussing that particular search strategy. Now, how to represent this node, whether A, S, T, Z, whatever you are seeing the different cities here, how to represent that particular city. So there are number of ways to represent the nodes. Okay, so basically the node and its properties you may consider as 5 components, you may consider as 7 components, you may consider as 10 components, but in this one we have considered it as 5 different components. The first one is the state in the state space. State means our starting point is our initial state. Our initial state is A, so that is one of the component. Okay, next is the node in the search tree that generated this node. If I ask you about node A, is there any node which generated A? Your answer is no, because A is your starting city or initial city. There is no root of A. Your beginning point, you will not find any node which is explored that particular node, because that is the initial state. Except that one, all other states having the root. Okay, which we call as a parent node, like A to S. So for S, A is a parent. Right? For S, A is a parent, but for A, there is no parent because it is the initial state. Now, we have to see the operator that was applied to generate the node. What operator you are going to apply on A in order to explore the neighbor city of A. Let's say the neighbor city of A is, as I discussed, that is called as STZ. Which operator you want to apply in order to explore S, T, and J? That also you require. The next one is the number of nodes on the path from the root to this node. Like we have explored S, right? We have explored S, we got F, we got O, we got R. So if you concentrate on F, how many nodes you have explored till now in your path? You have explored S, right? After A, you have explored, first you explored A, then you have explored S, then again you are going to explore F because your destination city is B. That's why it says that the number of nodes on the path from the root to this particular node. Or you can say simple term, we call that as a depth of the node, right? Or if you go for data structure, we call it the depth of the tree. The last data structure component is that the path cost from the initial state to node. Suppose you are traveling from A to B, right? A city A to city B. B is not explored yet. So in order to move from city A to city S, you have to pay some cost. In order to move from S to F, you have to pay some cost. If you explore F, if B is the neighbor city, you have to again pay some cost to reach from F to B. That's why we are calculating the path cost. A path should not be an infinite path. It is a finite path. So we want to see what is the cost you have incurred to reach that particular point, right? So these are the 5 different components you need to study when you represent a particular node. Now, as I said, there are some nodes are there which you want to explore. There are some nodes you want to explore in later stages. That's why you will see in the search strategy, there is always some nodes that is waiting to be expanded. Especially as I mentioned, open list and closed list. open list and closed list. If you go to the open list, you will find each and every element that is present in the open list, they are waiting to be expanded. Once it is moved to the closed list, it indicates that it is already expanded. Right? So such types of things are called as a frontier or called as fringe. Those nodes you have not explored and they are waiting to be explored, we call that as a fringe or frontier. Now, let us see what are the different strategies you have to follow in order to see the performance of the search strategy. So there are 4 different criteria you need to find for each and every search strategy. Okay. Or if you develop a new search algorithm or you go for existing search algorithm, when you talk about the performance, you need to consider these 4 criteria. First one is called as a completeness. Completeness says, is that starts a search strategy guaranteed to find a solution when there is one? When you solve a particular problem, you should know whether there is a solution to that particular problem or not. Because there are some solutions exist in the world which are not solvable. Like one of the problem, you know, whether P is equal to NP in the complexity theory, right? Whether P is equal to NP or not, that we don't know. Right? So you have to ensure that if there is a solution, then only one can achieve it. That's why it says that guaranteed to find a solution if it exists. If there is no solution, then we don't know. But if there is a solution exists, then you have to find that one. Then only you can say that search strategy is following or satisfying the completeness property. Obviously, the next one, next to our obvious one, you know, we are always calculating when you talk about algorithm. One is called as time complexity, which says how long does it take to find a solution. Okay, not with respect to execution time, but with respect to the loops, where the statements you have written to find in the process, right? By looking into that, you can say what is the complexity. Similarly, you want also space to keep the things. So you have to see how much memory does it need to perform the search. Generally, we assume that the source space is very large. So similarly, we also assume that the memory is also infinite. But in real life, the memory is finite. Like I will tell you a search, you apply a search strategy such that maximum you can keep 3 elements. You cannot store more than 3 elements because you have limited memory. Right? In that case, space is a major role, right? But normally, in case whenever we deal with the algorithm, we assume that we have sufficient amount of memory. The last criteria is called as optimality. Optimality says that does the search strategy find the highest quality solution when there are several different solutions. For a particular problem, you may find a number of solutions, right? Even if the number of, once you get the number of solutions, all the solutions value may be equal. Like you are solving a mathematical problem, there are number of ways to solve that particular problem, but finally you are getting the same thing, right? So in that case, you have to see what is the computational need of each and every method. If computational need of one method is higher, it is not good in comparison to those methods that require less computational requirement. So here it says that one angle it says that if number of solutions are there, then you have to find the highest quality solutions. So 5 solutions exist, you have to say that no, this solution is better than all the other solutions, other 4 solutions, or out of these 5 solutions, this solution is the best solution. That is called as optimality. So any search strategy you follow, right? Searching algorithm, you have to first look into these four factors: completeness, time complexity, space complexity, and optimality. So let us discuss one by one algorithm. I will tell you today 10 algorithms, okay, with an example, and all these 10 algorithms will analyze in terms of these four parameters. This is the overall goal of this session. As I said, all the search algorithms are categorized into two parts. One is called as uninformed or blind search. Blind search means you have no information. Okay, so here you can see blind search indicates that no preference is given to the order of successor node generation and selection. What is the meaning? Like your start city is A, right? You have explored the neighbor city of A. The neighbor city of A is S, T, and Z, right? What it says, no preference is given to the order of successor node. Who are the successors here? The successors are S, T, and Z. So whether to check STZ order or TSJ order or ZTS order, you will not give any preference, right? Not only node generation, but also selection of the node. Whether to select node S or T and Z, you have no preference. When apply hit and trial method, that is different thing, but you should not give any information. You don't have any information to select that one, node generation and node selection. So under this category, you will find 5 different search algorithms, starting from breadth first search. So you know, is a computer science. If you belongs to CSE, then you know this is a very famous search algorithm. There is another famous algorithm that is called as depth first search that we have studied in the data structure. But you will see the variants of this DFS, depth first search, and BFS, that is called as breadth first search. You will find another 3 algorithms. One is called as uniform cost search, depth limited search, iterative deepening search. Okay, so these are the 5 search strategy we will see. In addition to that, we will see another search strategy that is called as a bidirectional search. These all strategies are unidirectional, one way only. But when you go for bidirectional search, you will find searching takes place from both sides. Okay. Now come to the informed search. Let us see how a informed search strategy is different from uninformed search strategy. So if you go for informed search, some information about the problem space is used to compute a preference among the children for exploration and expansion. Take the same example. If I expand A, I got S, T, and Z, right? So whether to give priority to S or T or Z, you have some information. Right? You have some information to either select S or to select T or to select Z. There may be cost, it may be the distance between 2 different cities or the connectivity between 2 different cities. Such type of information is available to you. So blind search strategy is not explorable. You are not aware of the state space. But when you go for informed search strategy, you have some information. So under informed search, we'll see heuristic function. We'll see how to define a heuristic function, how heuristic function helps us to explore a particular node and select a particular node. Then we'll see another search strategy that is called as best first search. It is taking some parameter to select a particular node. Like if I give you the distance between 2 different cities, okay, 2 different city, or as I talked about Romania map. In Romania map, there are 20 different cities are there, or 19 different cities are there. If I give the data related to how these cities are connected and what is the distance between any two cities, then you can easily perform a search. One of the simple search strategy is called as best first search. But best first search having some limitation, it is because it is not considering one of the factor that is explored in the A star search. Okay, A stands for AND search, right? Then the improvement over A star search is called as AO star search, that is called as AND OR search, right? So sometimes your problem has more than one objectives, right? You can choose at a time, you can choose more than one objective to solve that particular problem. So at that time, AO star search will help you. The next one is hill climbing search. Hill climbing search is if you go to the Play Store, you can find there is an application called hill climbing, where you have to ride a vehicle in the hill area. The same concept applied here, that is called as hill climbing search. We'll see in detail about this. Okay, so this is all related to the definitions and what are the source strategies we are going to discuss in this session. Anyone having any questions related to on-informed search and informed search? Okay, I'll discuss one by one. Starting from the first search strategy, that is called as BFS, or called as breadth first search. What we will do in the breadth first search? You are given with a city map, right? As I said, city map. You know the distance of one city to another city, okay? And you have to explore one node or one city. Then you have to start roaming from one city to another city and cover all the cities, okay? So in order to do that one, what you have to do? First, you have to place the start node S on the queue. Start node S is nothing but the root node that you have to put into the queue. Then if the queue is empty, means if all the nodes are explored, then you have to return failure and stop. Your process is done. If the queue is not empty, then you have to pick the first element on the queue. Let that node is the goal node G. You can say if the first element on the queue is your goal node, right? You are searching for a goal. Like we are searching from a city start city A to reach to another city B, right? So if in that queue you found that the first element is only B, which is your target node or target city, then you can say it is successful and you have to stop. But if the queue is empty and you have not found your goal node G, then you can say it is a failure and you have to stop. Okay, if neither of the condition exists, this is not your goal node, okay, then what you have to do? You have to remove it and expand that element from the queue and place all the children at the end of the queue. Okay, you have to remove one node. Like I removed, let's say A. Let A is there in the queue. I have removed A. I have explored A. I got S, T, J are the three different cities that are connected to A. So they are nothing but the children of A. I put S, T, J into the queue. And this is removed. Okay. And you can follow any order. I'm not saying you have to follow S, T, Z order. You can follow any order to place these elements in the queue. Okay. And this process is repeated until unless you get your goal node G or the queue is empty. Right. So let us take an example. Like here, there is a tree is given to you. Let us assume that these are the different cities and these are the connectivity. A is connected to B, B is connected to D and E, A is also connected to C. C is connected to F and G. So now what happened? I have to first choose the root node A. In the previous step, previous slide, I told you, place the start node S on the queue. Okay, start node is A. I have placed in the queue. Now what I have to do is A is your goal node. Let's say my goal node is G. So A is not equal to G. What I have to do? Then first I have to remove A and I have to expand it. Right? We have to expand. So those nodes which are waiting to expand, they are called as a fringe. So fringe is a first in first out queue, that is new successor go at end. Okay. So first I have to explore the node A. If I explore A, then what I will get? I will get two other node that is called as B and C. You can see here. You have to remove A from the queue and you have to expand it. Then you will get the children of A, that is B and C. Right? What it means? It means that all the nodes at the depth D, suppose I consider the depth is D. The depth is, let us consider as a D in the search tree, right? All the nodes, for example, this is your depth D plus 1. This is your depth D. This is depth D plus 2. So all the nodes at the depth D, right? Here it is only one node, is expanded before the nodes at the D plus 1. Right? When you go to the depth D plus 1, the nodes that are present in the depth D, they are expanded. Similarly, when you go for the depth D plus 2, the nodes that are present in the depth D plus 1, that is expanded. Okay. So in this way, you can solve the problems in the breadth-first search. Right? For example, if you go for this exploration of A, you got B and C, and B is also not equal to G if goal node is G. C is also not equal to G. That means at depth D, you have not found your goal node. At depth D plus 1, you have not found your goal node. What you have to do? You have to go for depth D plus 2. So in depth D plus 2, you found the elements are D if you expand B. If you expand C, you will get the node is F and G. Okay. First you have to expand B. You got D. And again, D and E, they are also not your goal node. Then you have to expand C. You got F and G. F is not your goal node, but G is your goal. Right? So this is nothing but one level wise we are going to perform the search. We are not doing the search based upon the depth, based upon the breadth where we are doing the search. Now, if I evaluate the performance, okay. So I told you there are 4 search strategies. One is time complexity, another is space complexity, completeness, and optimality. So before defining these two, let us take some variable. Like B is called as the maximum branching factor. What do you mean by branching factor? Suppose one node is expanding, you are getting 2 children node. So the branching factor is 2. If you are expanding one node, you got 3 children. That means your branching factor is 3. If you expand a node, you are getting 4 children. Then your branching factor is 4. So we are considering here maximum branching factor in a search tree. If you go for a binary tree, generally it is 2. Then you have to choose, you have to also know what is the depth of the least cost solution. Whether your solution lies in this particular depth, or you need to expand again another depth, or you need to expand another depth. So D represents the depth of the least cost solution. And M is the maximum depth of the state space. Suppose the maximum depth of the search space is, let's say, this level. This is D is equal to, let's say, 0. This is D is equal to 1. D is equal to 2. This is D is equal to 3. Right? So now, with respect to these three, you have to say whether by taking these three variables, you have to say whether this BFA strategy is complete or what is the optimality of this search strategy, search algorithm, and time complexity as well as space complexity. So if you see about completeness, what completeness says? Completeness says that if there is a solution exists, okay, in a particular problem, if there is a solution exists, then you should guarantee that you are able to find that solution. Right? So in that first search you can get it, right? You will go for one level by another level, one level by another level. Definitely in one level you will find, if B is finite, then definitely you will get. If B is infinite, you will not get. Right? Suppose branching factor is infinite, if you take, then your search will never end. You will not get the searching element, you will not find. You will not find your goal node. Then coming to the time complexity. What is the time complexity here? First node, there is only one node. Then if branching factor is 2, there is 2 node in the next level. If the branching factor remains same, okay, remains same, then here you can see, if I expand this particular node, again 2 children are generated. If I expand this particular node, another 2 nodes are generated. So how many nodes are there? It is b to the power 2. That is 2 to the power 2, it is 4. So in this way, if you see, it is 1 plus b square up to b to the power d. So it is order of b to the power d. This is the time complexity. And if you go for space complexity, is also order of b to the power t, because you have to keep every node in the memory. Each and every node you need to keep in the memory. Now, what about optimality? Optimality says that if there are number of solutions are there for a particular problem, if you have number of solutions, then you should find the highest quality solution. Right? So in this case here, you can see optimality is yes, but it is subjected to if cost is equal to 1 per step. Otherwise, it is not optimal. In general, it is not optimal. Right? There are a number of ways to reach to the particular node, right? So if you take a cost is equal to 1 per step, then only it is optimal. It is also not important to note here that it is optimal to provide the path cost. It is optimal provided the path cost is a non-decreasing function. Non-decreasing function means each and every path has some cost, right? So if the path cost is a non-decreasing function, note that when you write 7, 8, 10, 12, it is in increasing order. 7, 8, 10, 12, they are in increasing order. But when you go for 7, 8, 8, 10, 11, 11, 12, they are not in the increasing order. Rather, you can say it is a non-decreasing order. Right? So, this is a non-decreasing function, then it is optimal. Right? Because sometimes the costs are not in that particular, not following that particular non-decreasing function. Then in that case, you will not find the search is optimal. Okay, now you see, with a given value of B and a given value of D, what are the total number of nodes in a particular tree? Well, why I am saying this one? The reason is that you have to store these nodes, so you have to think about memory. Okay, like if the branching factor is 10, Branching factor is 10 means one node having 10 children, at max 10 children, right? 10 children. And if depth is equal to 2, the number of nodes in that particular tree is b to the power 1, right? b to the power 1, sorry, 1 plus b to the power 1 plus b to the power 2. So if you put here 1 plus b is your 10, so 10 to the power 1 plus 10 to the power 2. So the total number of nodes you will find here, it is 1 plus 10 plus 100 is equal to 111. Right? So see, with a depth level of only 2, only the branching factor will increase to 10, right? So the number of nodes is 111. Suppose in order to search each and every node, if you roughly see that one node is taking, let's say some time. Definitely, when you search a particular node, it will take some time. Okay, so imagine if the time is some nanosecond or some millisecond. So total time required is 1 second. 1 second is a feasible solution. And the memory requirement is 11 kilobyte. That is also feasible. But when you go for higher number of nodes, like you can see here, when depth is equal to 14, the number of nodes is 10 to the power 14. So how much time required to explore a particular node? A single node takes 1 millisecond, I told you. So if you go for 10 to the power 14, then it took 3,500 years to complete the search. Right? Human life is not that much, right? So 3,500 years it will take to complete the search. And how much amount of memory is required? The memory requirement is 51 terabytes. That's why the memory requirement is one of the biggest problem for the breadth-first search. Right? So in order to avoid this particular problem, we have another kind of search that is called as uniform cost search. So uniform search is a modification of the previous search strategy that is called as breadth-first strategy. Okay. So what it says, what breadth-first search is doing, it is going level by level, right? So it is saying you have to expand the lowest cost node in the fringe. So if there are 5 nodes are waiting in the queue, you have to choose the node which is lowest cost. Fringe means the nodes that are waiting in the waiting and they are not responded, not expanded. So you have to choose the lowest cost node. Okay. So let us see, for example, if you take this particular picture, let's say this is your figure A, this is your figure B. Okay. Figure A shows that the complete search or the number of nodes available in a graph, or you can say tree, right? If they are not connected, then only you can say a tree, right? Or you consider simply a graph. So now this is your source is represented as S, and this is your goal that represented G. So when you expand S, what you got? You got A, you got B, you got C. When you expand S, you got A, B, C. So earlier S is there in the front of the queue. That's why you have removed S and you have expanded. You got A, B, C. Now you can put A, B, C in this particular queue. Right? So out of A, B, C, these all are called as fringe. So you have to choose the lowest cost node on the fringe. Lowest cost node among A, B, C. So you should know the cost. Suppose the cost is 1, 5, and 15. You have some information. So obviously you will choose the lowest one, that is A. So when you expand A, you got ABC. The cost of A is 1, cost of B is 5, cost of C is 15. So you have to choose the least cost. The least cost is A only. So when you expand A, okay, when you expand A, so you can see here, when you expand A, there is only one node, that is G. So you reach to the goal with a cost of 11, because this is 1 and this is 10. This is 1 and this is 10. 1 plus 10, you got 11. Right? So your path, you can say this is SAG is your path, right? If you follow the lowest cost node. But if you see carefully here, if you follow SAG as your solution, this solution is not the optimal one. Why? Because if you choose S, B, and G, S to B, the cost is 5. B to G, the cost is 5. So total, the cost is 10, which is less in comparison to the previous one. Previous one, it is 11. But in this case, it is 10. But why you have selected SAG? Because you have seen the least cost from S to any other neighbor node is A. That is 1. Right? Although it is not an optimal one. Okay, first one, because the second one provides the optimal M in comparison to the 3, all 3. Now, the goal is checked if you go for SBG, because previous solution gives 11, this solution is giving 10. But if you go for the next solution, for example, if you go for SCG, so it is 15 plus 5. So the path cost is very high in comparison to the previous one. So if you see here, we have considered the path cost is all values are not negative. These values are positive values. So if every operator is non-negative cost, because when you take a graph, there are some edges where the cost is negative also. In the previous case, we have seen the path cost is positive, but in the graph, the path cost may be negative also. So if every operator has a non-negative cost, then definitely the cost of the path will increase. When you go ahead in a particular path, definitely your cost is going to be increasing. It will never decrease. But when you go for a negative cost, like S is there, A is there, G is there, let's say S, B, G is there, S, C, G is there, right? So here the cost is 1, here it is 5, it is 10. That's why I've selected SA, right? Okay. So now suppose this cost is -1, right? Then SAG leads to 0. You can reach to the goal with 0. Suppose here the cost is -3. So you can reach the goal by 5 minus 3, that is 2. That is another solution. That's why when some operator, if the operator also considers the negative cost, then in that case, it is very difficult to find which path is your optimal. For that reason, what you have to do, you have to perform exhaustive search. Exhaustive search is nothing but called as brute force search. Brute force search says that you have to go for all possible solutions and find the best solution among that values, right? That solutions. Out of all paths, you have to select one particular path, right? And if you look into the properties is same as your uniform cost search. Now, coming to the third search strategy, that is called as depth first search. Also, you may be aware of this particular search strategy if you have studied the data structure subject. So what you are doing here, instead of considering the breadth, you are considering the depth. So first you have to place the start node S into a cube. Okay. And if at any point of time you found that the stack or the queue is empty, right, the implementation is stack. But if it is empty and you have not found your goal node, that indicates that it is a failure. You have to stop here. But if you found that S is not your goal node, then what you have to do? You have to remove it, right? If you have to remove it. If it is your goal node, then it is success, right? If the first element on the queue is goal node, then you will simply declare that it is success only. But if it is not a goal node, then what you have to do? You have to remove it and expand this particular node. And whenever you are expanding a particular node, you may get more than one element. And you have to place the children at the front of the queue. Suppose I am exploring S, I am getting, let's say, X, Y, Z. So I'll put these children in the front of the queue. Generally, in the queue case, we add the element from the rear part, right? That's why the implementation for this particular algorithm is stack, not the queue, right? And this process you have to repeat unless you find your node or your search is failed, right? So depth first search is actually faster than the breadth first search. That's why people prefer DFS in comparison to BFS. Okay, so let us see one example. Like this is a tree is given to you, right? So instead of taking a first in first order queue, here we have considered LIFO queue. That is called is last in first out queue. What I have to do here? I have to expand A. When you expand A, because A is the node that is available for you, right? It is there in the queue. You have to expand A, okay? Because A is not your goal node. So once you explore A, you got the children node is B and C. The children node is B and C. So what I have to do? I have to put B and C any order at the beginning of the queue. Then B is not my goal node. So I'll remove it and I'll expand. When I expand B, I got D and E. And D and E I'll put at the beginning of the queue. The only difference is that in the previous case, we are considering level by level. Here we are not considering level by level. Instead of that, we are considering one node in each and every level. Right? See here, we have expanded A, we got BC. And we have expanded B, we got D. We have selected D, not E. We have selected now, we have selected A, B, then again we have selected D. We have expanded D. We got H and I, right? H and I. Then we check that whether H is our goal node or not. H is, let's say, our not goal node. Then we'll go for I. H is not my goal node. That's why I'm searching I. So till now you can see if I consider the depth, this is depth 0, depth 1, depth 2, and depth 3. So you can reach depth 3 with only reading 4 nodes: A, B, D, and E. Sorry, this is H. This is H. Right? Only by reading 4, you can reach to the leaf node. Right? But if you found that H is not your goal node, then you have to go for I. Okay. If I is not your goal node, again you have to go for E. Like that, this process continues. Then you have to expand E again. When you expand E, you will get again J and K. You check whether J is your goal node or not. If not, then you have to go for again K. If K is also not your goal node, then you have to go for another branch, that is C. Again you expand C, you will get F and G. And when you expand F, you will get LM. Check whether L is your goal node or not, or M is your goal node or not, right? In the similar fashion, if LM is not your goal node, you will go to G, expand G, you will get NO. Check that N is your goal node or not, or O is goal node or not. Like that, this process continues. Okay, this process continues like this in the depth first search. Now, if I ask you the same 4 question, what are the search strategy? What are the values of the search strategy in the case of depth first search? Let us come to the first one. Whether this search is complete or not. Complete means if there is any solution, okay, if there is a solution, whether we can achieve that particular solution or not. The answer is no. If there is an infinite tree, right? If the tree is infinite, then you may, if you are going in a wrong path, definitely you will not able to reach your goal. So in the case of infinite depth search, depth space, this DFS search is not complete. Okay. And what is the time complexity? The time complexity is order of b to the power m. Okay. If the maximum depth you can consider is d, and if m is much more larger than the d, then only you can say it is order of b to the power m. And space is order of bm to keep the elements, and it is not optimal. Right? It is not optimal because you have to place the children in any order. Okay. If you are lucky enough, the node that is present in the front of the queue, okay, that is leads to you, leads to the goal node. If that is not leads to the goal node, then definitely it is not, you will not get your solution easily. And it can stop at going down in a wrong path. If there is a wrong path, definitely you will not find your solution. So depth first search should be avoided when you know that the search tree with large or infinite maximum depth. If in a particular search space, if you see the number of the length of the tree is very high, okay, or you have infinite maximum depth, in that case you have to avoid depth first search. There is another search which in extension of your depth first search, that is called as depth limited search. So what is there in the depth limited search? You know that in depth first search, if the depth is high or it is an infinite one, definitely you will not get your solution. So depth limited search avoids this pitfall by imposing a cutoff on the maximum depth. I'll give you a cutoff, right? You can go up to the depth level 3, you will get your solution, right? For example, as I said, we are discussing about the Romania map. In Romania map, suppose there are 20 cities. So if there are 20 cities are there, right? So the what is the maximum path cost? Maximum path length. The path length maximum is 19. Right? If there are 20 cities are there, you start from a particular city, and if you see the path, the number of cities you will cover, excluding your source source city, is 19. Right? But when you go beyond 19, what you will say? Your search is going in a wrong path, or there is a loop in your path. That's why you have not reached to your destination city, even if you exceed 19. Right? So, like in Romania map, at max you have to visit 19 cities to reach to your destination. Right? So we are guaranteed to find the solution if it exists. So in comparison to your depth first search, if you ask about the completeness, this search is complete. But if the depth limit is greater than the general depth, that is D. If I say you will find your solution in depth level 3 and you got within that limit, then only you will say your search is complete. But when you choose the depth limit is too small, then it is not complete. Similarly, optimality, there is no guarantee of optimality because you may get the solution, but you cannot claim that is the highest quality solution. Okay. What is the time complexity here? The time complexity is order of b to the power L, where L is the depth limit. The previous case is order of b to the power m, because you have taken m is generally much larger than the d, but here we have considered depth limit is L, so it is order of b to the power L. Similarly, space complexity is order of BL. Okay, so these are the different values for the search strategy. Coming to the last uniform blind search, uniform or blind search, that is called as iterative deepening search. So the main problem in the depth limited search is also to choose a particular limit. If you choose a lower limit, then you may not find the solution. If you choose a higher limit, then again there is an issue that you may go to a long path to find your solution. Okay. So here if you see, if you take the Romania map again, where there are 20 cities are there, if you see that particular graph, okay, or that connectivity, you will find at max you have to visit 9 cities if you want to move from one city to another city. Okay, alternatively, you can say we would discover that any city can be reached from any other city at the most 9 steps. Although there are 20 cities, worst case it is 19. But the way they are connected to each other by looking into that, you can say at the most it is 9 steps. Because the diameter of that particular state space or the Romania map, it is 9. So what iterative deepening search is doing here? So this strategy starts with the depth 0. It explores all the nodes. If depth 0 you have not found the element, it will go for depth 1. If depth 1 also you have not found, you will go to the depth 2. Okay. But the order of expansion of the states, if you see, it is same as the breadth first search. Level wise, you have to explore all the nodes of the level before moving to the next level. Right? But it is wasteful because there are so many states are expanded multiple times. So let us see one example to understand this iterative deepening search. So I have taken, let's say, limit is equal to 0. If limit is equal to 0, then only root node is going to come. If limit is equal to 1, you can expand the root node and you can get 2 children node. But when the limit is 2, again you have to start with the root node, expand that root node to get 2 children node, expand one of the children node, expand the other children node. This process you have to carry out for each and every limit. Like here you can see the same process. For limit 0, you did this one. For limit 1 also, you are repeating this one. For limit 2, you are repeating this one. For limit 3, you are repeating these things, right? The same thing you are repeating. That's why it is wasteful. But if you compare with your depth limit search, so if you go for your depth limit search, when you consider the branching factor is B and the depth is D, so number of nodes explored is 1 plus B square up to B to the power D. So if you take B is equal to 10, D is equal to 5, if you put in this particular formula, then it is 1 plus 10 square plus 10 cube plus 10 to the power 4 plus 10 to the power 5. So number of nodes you have to expand with this branching factor and depth is this much. But when you go for iterative deepening search, what you have to do? You have to repeat B to the power D 1 time, B to the power D minus 1 2 times, B to the power D minus 2 3 times. Okay. Similarly, B to the power 2 D minus 1 times. Right? Like that you have to repeat. So with the given value of B is equal to 10 and D is equal to 5, to compare the performance of the depth limited search and iterative deepening search, you will see the number of nodes you have to expand. It is 1, 2, 3, 4, 5, 6, which is 11 times more than this one. That's why the iterative deepening search is wasteful. Because so many states you have seen here, they are expanded multiple times. Right? Now, if I ask you whether this is complete, yes, it is complete. Right? If you go explore all the nodes, definitely it is complete. Is it optimal? Definitely you are going to find the solution and the highest quality solution. That's why it is optimal. What about time complexity? Time complexity is order of B to the power D. Space complexity is linear space, that is order of B to the power B into D. Right? So iterative deepening is the preferred search method when there is a large search space and depth of the solution is not known. Can apply only if when you don't know that in which level it is available. Okay, like depth limited search, you put a limit of, let's say, depth is equal to 3, but your solution is presented depth is equal to 4. Then gone. It is not possible. Depth is equal to 3, you have said, but depth is equal to 4, your solution is there. So you will never reach to that particular solution. So that type of problem we can avoid. Now, the sixth algorithm, which I have not listed in that list, that is called as bidirectional search. It is another important search. So in bidirectional search, what you have to do, you can see in the previous searches like BFS, DFS, depth limited search, and iterative deepening search, uniform cause search. You can see we only go through the search strategy from the root, from our initial state. But bidirectional says that you have to start search from both sides. One is forward from the initial state, backward from the goal. Suppose this is your source and this is your destination. You have to start the search from source as per the previous 5 algorithms. But bidirectional says that you have to start from S. Also, you have to start from D. Right? For example, one of your friend is at New Delhi. Right? Another friend is there at Kanyakumari. Right? So what you would ask to your friend, let us meet at an intermediate position, let's say Hyderabad. So the first person has to move from New Delhi to Hyderabad, and this destination person has to move from Kanyakumari to Hyderabad. Okay, so forward from the initial state, backward from the goal state. And when you meet in an intermediate point, then you have to stop the search. So instead of the complexity is order of b to the power d, what we are doing, the depth is now divided by 2. So we call the complexity is order of b to the power d by 2. Because we did not go for all the depth, right? First search is up to d by 2. Second search is also up to d by 2. So forward and backward searches each have to go only halfway, right? So what are the main issues in the bidirectional search? If you see, somebody may ask you, when we are not sure that where is the depth, where is that goal node, in which depth, what is the meaning of to say that backward from the goal? Once you don't know where is your goal, in which depth the goal is present, there is no meaning to say that the search backward from the goal. Right? That is the first issue. Second one is, when all operators are reversible, the predecessor and successor sets are identical. So calculating predecessors can be very difficult. Like we always say that we expand a particular node, we generate a successor. But what you have to do in bidirectional search, you can generate your predecessors. In child can generate your parent, which is not possible. Right? So that is also one of the criticism related to the bidirectional search. And what can be if there are many goal states? Instead of one goal state, if you have multiple goal state, then where to meet? Like I told you, there is a multi-agent problems are also there. In multi-agent problem, you are dealing with more than one agent. If you go for multi-goal, you have number of goals. So each and every goal you have to start the search. So it will be very difficult to reach to a particular point, right, where you can find a particular solution. Right? So this is the picture you can see. This is the start point and this is the goal point. We expected to meet in an intermediate point. That's why we call that the complexity is divided by 2. Order of b to the power d by 2. Space complexity is also order of b to the power d by 2. But whether this search is complete? Yes. If there is a solution, you will find the solution. And is it optimal? Yes, it is optimal. Because if the number of solutions are there, you can find your highest quality solution. But the problem is that sometimes we avoid the repeated steps. Like I told you, you have taken a city A, you have expanded that city, you got STZ. You have selected S, and you have, when you expand again, A is coming. So by mistake, if you choose A, then this ASA is in a loop, right? One of the example we have seen also in my first lecture, that there is a problem that is called as missionary and carnival's problem. In missionary carnival's problem, we have to move from one side of the river to another side of the river. So in that case, the number of stops, if you see the solution, you will find the number of states are repeated. Okay. Suppose you are moving from one side river to another side of river. In between also, you are again moving from that side to the other side. That's why this is called as repeated states. So the space contains only m plus one state when m is the maximum depth. So in order to avoid the repeated these states, what you can say, do not return to the state you just came from. Like if you say, when you expand A's, you will say, don't return to the state just you came from. You came from A, so it should not come A as your successor. So that way you can avoid. Or you can say, do not create a path with a cycle in them. Suppose there is a path, but there is a cycle. Such type of things need to be avoided. Or do not generate any state that was even ever generated. Not only this type of problem happens here. When you expand A, you will get STZ. Suppose when you expand S, then you will get XYZ. Okay. When you expand X, and again you are going to get A. So in this case, you can say the state A is already generated, so A should not come here. So these are the ways to avoid the repeated states. Right? Is there any question till now? Okay, let us proceed. The informed search. So informed search, we will see best path search, we will see A star algorithm and AO star algorithm. We will see also hill climbing algorithm. So the main idea of this best path search is that it uses a evaluation function for each and every node. In the uninformed search strategy, we are not looking into that particular evaluation. That's why I told you there is no preference given to the successor nodes. Okay. And if you evaluate each and every node, then obviously you will expand the most desirable node, right? Those nodes which are not expanded. Out of that, you have to choose the node which is most desirable, right? Some of the cases you can see, which is called as a greedy search. Greedy search says that suppose you want to greedy about to find a particular solution. You're very interested to choose this particular path, not the other path. That is also one of the special case. A star search that we are going to see with an example, that is also belongs to a special case. Now come to the greedy search. Let us consider the evaluation function is h of n. Okay, the evaluation function is h of n. We have to estimate the cost from n to the closest goal, right? So when you expand A, what you have to see, you have to calculate the estimate cost for A to S, estimate cost from A to T, estimate cost from A to Z, right? And once you reach to S, again you have to see the cost from S to destination. If you choose T, you have to find the cost from T to destination. If you choose Z, you have to find from the cost from Z to your destination. Okay. So in order to simplify this one, here we consider h of n as a SLD. SLD means straight line distance. Okay. Our intention is to solve the problem to reach from a city A to city B in a Riemannia map, and you are given with the straight line distance. So greedy will, what it will do? whichever path is minimum, it is going to choose that one. It is not looking into what are the distance you have covered till now, right? So greedy search expands the node that appears to closest to the goal, but it is not keeping that what are the cost you have spent to reach to that particular node. So we look into two basic approaches here. First one, to expand the node closest to the goal. Second one is to expand the node on the least cost solution path. Okay, so let us see one example. So this is the Romania map. Okay, you can see there are different cities. They are represented. The cities are represented by a square, and the communication between the cities is represented by line. And this is your source city. This Arad is your source city, and your destination city is Bucharest. Right? Your objective is to move from A to B using best first search. And distance, straight line distance to B is available here. That means what it indicates 366? 366 indicates that the distance, straight line distance between A and B. The straight line distance from B to B is 0. The straight line distance from C to B is 160, and so on. Okay, I hope it is clear. Right? There are different cities are there. Their straight line distance to the city B is given here. Okay, let us see one by one. So first our source city is Arad, right? What is the distance from Arad to B? Bucharest. Can anybody tell? Distance from Arad to Bucharest. What is the straight line distance? What is the straight line distance? The straight line distance is 366. Okay. So I have written here 366. You can find here, right? The first value is 366. So it is nothing but the estimated cost of the cheapest path from that particular state at node N to the goal state. Means Arad to Bucharest. The distance is 366. Okay. Now what I have to do? I have to expand Arad. If you expand Arad, what you will get? You will get this city T, this city S, this city Z. Okay. But what is the distance from S to B? You see here, what is the distance from S to B? 253. You can see here, I have written here 253. What is the distance from T to B? T to B is 329. Here you can see the value is 329. What is the distance from Z to B? 374. Here you will find 374. So one thing you can notice here in the best path search or greedy search strategy, we have not included the cost from A to S or A to T or A to Z. We have only considered the distance from S to B, T to B, and Z to B. That is the only difference between the best path search and A star search. Right? Now what I will do, I will expand. Which one I will choose out of this S, T, and Z? S, T, Z, I will select 253. S, T, Z, I have to choose 253. Right? So find the neighbor city of S. The neighbor city of S is O, also A, also R, also F. So you can see here Arad, then this F, O, and R. Now you tell me A to B distance is 366. That you know, but we have to exclude it because it is a repeated state. Now what you will do? You have to find the distance from F to B, O to B, and R to B. What is the distance from F to B? F to B is 178. So it is not 176, it is 178. Okay. The distance from O to B, 380. So you can see here 380. The distance from R to B, the distance from R to B is 193. Right? So once you found this one, what you can say, which one is minimum? The minimum is F only. So I am expanding F. So if you expand F, what are the cities you will get? You will get S as well as B. Right or not? Right? You got S and B. Then from S to B, what is the distance? S to B, the distance is 253. And what is the distance from B to B? 0. One is 253, another is 0. So you reach to your destination B through this particular path, Arad, Sibiu, and Agras and Bucharest. That is A, S, F, B. Right? This is the path to reach from a city A to city B. But you can see here it suffers from the same defect as the depth first search. You can find your solution, but it may not be a optimal solution. And sometimes it is incomplete also, because it can start down to find an infinite path. Suppose in case this value is lower, 366, then there is a loop. So you may reach to an infinite path. You will not reach to the solution at all. Right? So if you see, the worst case time complexity is order of b to the power m, where m is the maximum depth of the search space. And you can see here, although it is not optimal, but you are getting one solution. But the problem why you are not getting optimal is that you have not considered the cost incurred to reach a particular path. When you reach to S, you have not seen what is the cost incurred A to S. When you reach F, you have not considered the cost from A to S, S to F. When you reach to B, you have not considered the cost from A to S, S to F, and F to B. That is the reason why this is a problem. And space complexity here also, it is order of b to the power m. Okay, so that is the drawbacks of your best first search or greedy search strategy. Coming to next strategy, that is called as A-star search. So in previous case, we consider the evaluation function is h of n. But here we consider evaluation function is f of n is equal to g of n plus h of n. We added one more parameter, right? That is g of n. Previous case, if you ask what is the f of fitness for this evaluation function f of n, then that is only h of n, right? But in this case, in place of h of n, we are taking another one also, gn, along with that one, gn plus h of n. What is that? G of n says that it is the cost so far to reach the node n, right? And h of n says that what is the cost to reach from that node to goal. Like if you take an example, I told you New Delhi, let's say to Kanyakumari, right? Let's say intermediate city is Hyderabad. So what you have to do in G of n here, you have to calculate the cost from New Delhi to Hyderabad. And you have to calculate the cost from Hyderabad to Kanyakumari. This is called as your G of n. This is called as your h of n. Together we call that as f of n. Okay. So let us see one example to clear the idea. Now what we will do here, we will again search from the city Arad to Bucharest. So when you expand A, you will get three different cities, that is S, T, and Z. But if you see here in Arad, while before expanding Arad, you have to calculate what is the G of n value. What is the G of n value? G of n is nothing but Arad to the current node. Current node is also Arad. So Arad to Arad, the distance is 0. And Arad to Bucharest, what is the straight line distance? The straight line distance is 366. So you got this value is 366. Total is 0 plus 366, you are getting 366 only. Now, when you expand A, you will get Z, S, T, right? Okay, when you expand A, you will get Z, S, and T, right? And what is the cost for A to S? By looking into this graph, you can tell what is the distance from A to S. That is 140. Okay, the cost, or you can say distance. A to T, it is 118, and A to Z, it is 75. So these values are called as your G of n. But what is H of n? H of n is nothing but the straight line distance from Z to B, that is 374. The straight line distance from S to B, it is 253. The straight line distance from T to B is 329. Can anybody sum and tell me what is the value? 374 plus 75. How much it is coming? You will get 449, right? If you sum these two, you will get 393. If you sum these two, this is, you will get 447. Okay. Now you tell me, we consider h of n and h of n and g of n. We found f of n, right? Which one is minimum among these three? The minimum among these three is this one. That is 393. Right? So now if I expand S, what I will get? I will get O, I will get F, I will get R, I will again get A. Right or not? So let us see. This we have done. When I expand S, I got A, F, O, R. Then how to calculate the cost? The cost you will calculate if you take Arad to, if you see Arad to A to S, what is the distance? 140. So this cost is 140. A to T, what is the cost? A to T, the cost is A to T is 118. The cost from A to Z is 75. Right? You can see this is the value. But you have decided to expand S because S is least cost among all the three. This is the least cost, right? Now, what we will do? S to A, what is the cost? Again 140. Because you know this is 140, this is another 140. S to F, what is the cost? S to F? S to F, it is 99. S to O, what is the cost? S to O, it is 151. Right? Now, S to R, what is the cost? S to R, it is 80. Now, you can see the first value, how it is coming to 80. This is 140 plus 140, it is coming to 80. 140 plus 99, you will get 239. 140 plus 151, you will get 291. 140 plus 80, you will get 220. Now, what you can do, you have to again find the distance from A to B, F to B, O to B, and R to B. And these are the values you will get if you apply straight line distance. Right? So after calculating the f of n by taking g of n and h of n. What you are getting? You found that the f of n of which one? R is the better one, right? Because R is 413, F is very close to R. So next city that you want to expand is R. So if you expand R, again you are getting C, P, and S, right? Again you have to calculate all the values, right? This is 140, S to R. S to R, the cost is S to R is 80, and the cost from R to C, it is 146, I think. So you sum these values. This is 140, 80. You will get 220. 220 plus 146. So you will get the value as 366. Right? So out, similarly, you have to calculate 140 plus 80 from R to P. R to P, what is the cost? R to P, what is the cost? 97. So this is 97. So if you add, then you will get the value as 417. Right? So like that, if you proceed, you will reach to the city B. Right? Like here you can see, till now you have not reached to city B, but the lowest cost here is P. So the next node you are going to expand is your P. Right? But you can see here, I'm showing you another example. Okay, there is a small mistake here. If you see, this is 417, 413, and this is 417, right? That is the reason you have expanded R. Right? If this is 4, if you calculate it, there is a mistake here. This is not 176, this is 178. Then you will get this value as 417. But here you are getting the value is 413. That's why you have expanded R. Okay. Then out after expanding R, you found that P is the better path to expand from R. And when you expand P, you got the value is, there are 3 different cities, that is B, which is your destination city. So you have to go through R, S, then R, then P, then you will reach to the city B. Okay. But interestingly, you can see, suppose I will expand F. What is the cost you are getting? The total cost you are getting here is 418, right? The f of n value you are getting 418. Suppose instead of taking this one, this R, suppose I have selected F, because there is a close fight between F and R. This value is around 413 and this value is 417. You can say this 417, this path is nothing but a second best path, right? So if I expand this particular node, then I will get another 2 city S and B. So you can see I got B also. So here you are getting A, S, R, P, B. But here you are getting, if you follow this part, you are getting A, S, F, B. Right? If you consider the number of nodes wise without looking into this, so obviously this path is better. ASFB is better, right? Because the less number of intermediate nodes are there. But cost wise, if you see, the cost is coming as 450, right? What it shows? It shows that A star search case, if you choose both H of n and G of n in order to determine f of n, whatever path you will choose, that is the optimal path. You will not get a better path than 418, this particular path. This is not a better path, right? Even if it is having less number of nodes, this path is not good, but this path is the better path, right? So this is the algorithm. You can go through this algorithm. As I said earlier, you have to maintain 2 lists. One is called as open list, another is called as closed list. First, you have to put the start node S on open. So let's say there is an open list. Okay, these are the nodes that are waiting to be expanded, and this is a closed list. First start node, you have to put in the open list. If open is empty, if there is no other node while you are running this particular algorithm, if there is empty, then you have to return failure and you have to stop. Otherwise, what you have to do, you have to remove from this open the node n, that is smallest value of f star n. Okay, you have to open the node n and you have to find the smallest value of f of n. F of n is nothing but g of n plus h of n. And if the node is a goal node, then you have to return the success and you have to stop. Otherwise, what you have to do, you have to expand S. You will get its successor. Let's say the number of successor is n days, and place this n on and place, generate all its successors, right? And move the S to the list close, because S is already expanded, right? As S is expanded, you have to put it in the closed list. Then what you have to do, for each and every successor, you have to repeat this particular process. But if n days is not already an open and closed, then you have to attach a back pointer to n, and you have to again calculate f days of n days. Okay, and for each n days that is already in open and closed should be attached to the back pointer, which replaces the lowest g of n path. Okay, what is g of n? H of n is your heuristic function. G of n is you have calculated how much cost you have incurred to reach to that particular node, right? So that you have to choose. And finally, if n days was closed, its pointer was changed, and remove it, place it in open. This process you have to do. Means that those nodes who are present, those nodes are placed in the closed list, they are fully explored. And those nodes which are present in the open, they are waiting to be expanded. These are the some of the conditions that A star satisfies. First one is called as admissibility condition. Admissibility condition says that the algorithm A is admissible if it is guaranteed to return an optimal solution when there is a solution exists. Okay. Second one is completeness condition says that already we know this one. When algorithm A is complete, if it is always terminates with a solution when one exists. Third one is a dominance condition. Like if you consider two different algorithms, A1 and A2, if you say that one complexity is order of n square, another complexity is order of nq, what you will say? Order of nq is dominating. Right? This complexity is, you have written a process, one process that is order of n square, another process it is order of nq. So overall complexity is order of nq only. Similarly, if you take two admissible algorithm A1, A2, their heuristic estimated function is, let's say, H1 and H2, H1 star and H2 star, then you can say A1 said to be more informed than A2 whenever H1 star n is greater than H2 n star for all n. If for every value, if A1 is better than A2, then you can say A1 is dominating, is said to be dominated. Okay, you take two algorithms, you run with a different set of input, and you found that the first algorithm is always giving the better performance or faster performance in comparison to the second one, then you can say one algorithm is dominating another algorithm. Similarly, we have optimality condition. Optimality condition says that algorithm is optimal over a class of algorithm if A dominate all members of the class. If there are multiple solutions that exist, and if you choose one of the solution is the best solution, then we call that as optimality. Now coming to the last part of this talk, that is called as local search algorithm and optimization algorithm, optimization problem. We'll see here also some of the game search. Like till now, whatever search strategy we have discussed, either a on-informed strategy or informed strategy. Okay, so if you see both strategy, whether it is a informed or informed strategy, you will find that we consider that the memory is not finite. But it will be more challenging when you have a very little memory. It is also challenging to find the reasonable solutions, because when you keep something into your memory, if suppose there is a path A, then if you explore it is BC, explore DE and FG. Now you see, if you keep A, suppose there is a memory size of only 2, you can keep only 2 elements. So you can start A, right? You explore A, then you have to put B, and you have to check that whether B is goal or not. If B is not your goal, you have to remove B and put C here, because I cannot place A, B, C, 3 things in my memory, because I have very little memory. Okay, so here we are interested in, when you go for an optimization problem, we are having an objective function, and we have also fitness function. Fitness function will tell you whether a particular solution is providing you a good solution or not. Objective function is going to guide you, but fitness function is going to give you a fitness value. By looking into this value, you can decide whether the particular solution is good or not. So if it is a minimization problem, our objective is to find the global minimum. If it is a maximization problem, our goal is to find the maximum value, right? So here you can see one of the search, very famous search, that is called as hill climbing search, right? I told you hill climbing games are also available in Play Store. So suppose your current state is here, and if I say you can take delta is the step length, right? Your current state plus delta is your next state. Let's say your next state is here. So there is a change from the state to here. This change in the state you can do if and only if the height of that particular hill is increasing, or it is same, then only you can do. So you will take this one, you will accept this your next step. Suppose next to next state is this one, then you will move to here because height is increasing. Next state is this one, you are moving to here. But once you reach to the top of the hill, then if you take a step length of delta, right, you will reach to a state where your height is not increasing. So we can say that is a solution, but we cannot claim that is our global maximum. You can claim that is a local maximum, but it is not a global maximum. Because if your solution is present here, your current state is present here, then only you can reach the global maximum, right? So you have to see that sometimes also if I choose the current state here, so once you reach to this particular state, if you take a step length of delta which reach to this particular position, your height is not increasing, but your height is same. If such a thing is found, then we call that as a soldier. Or sometimes we say that is a flat local maximum, because over this particular period you will find the same solution. Okay. Then, but if you go for this hill climbing search, you will find 3 different difficulties. Okay, the first difficulty is called as local maximum. Our objective is to reach to global maxima, right? But here we are getting local maxima based upon our state. So we can define a local maxima. It is a peak that is higher than its neighbor state. Like here you can see, this is a local maxima which is higher than its neighbor state, but it is not the global maximum. That is the problem. First problem with hill climbing. Second is you may get ridge also. What is ridge? Ridge is nothing but a sequence of local maxima. Here you can see the sequence of local maxima. Here you see in the soldier case, you may find a series of local maximum. That is also one of the issue. Another problem is called as plateau. So it is an area in the state space landscape where the evaluation function is flat, just like soldier. In that case, your function, evaluation function will be same, right? So these are the problems you will face when you go for hill climbing search. And the last search strategy is called as AO star search. We already seen A star search, but AO star says that end or graph. Like suppose a person needs a TV set. So what he can do? He can earn money by working hard. Then he or she can purchase the TV. So this age, you can see there is a line here, right? What it says, in order to possess a TV set, you need both. Only you can buy the TV, you can earn money. Then only you can purchase the TV. So both events need to be occurred. You cannot buy the TV if you are not earning money, right? Or as an alternative solution, you can say you can steal a particular TV. So if you look into these two conditions occur at the same time, but this condition is not occurred with any other condition, right? Now, if you talk about the particular tree, like cost of this particular node is 3, cost of this particular node is let's say 4. But what this it indicates, this is end one, right? If you see this and this is OR. But if you look into this is AND. That's why it is called as AND OR graph. Here the cost is 3, here the cost is 4. So the sum of this cost is nothing but 3 plus 4 plus 1 plus 1. By assuming that this age cost is 1. Okay. Similarly, if you take this particular T, here the cost is 5, here the cost is 10. The cost here is 5 plus 10 plus 1 plus 1. Similarly, if you look into this particular tree, this particular end part, it is 3 plus 4 plus 1 plus 1 and so on. So this is an example of your ender graph. Okay, now coming to the game search, like that the way you have seen the different kind of search, whether it is a blind search or unblind search, right? That is called as informed search. So when you go for different kind of game design, you will find there are multiple players, right? So you have to create an environment which is cooperative as well as competitive. Means the move of a particular player, it is going to affect another player. Obviously, when we see that a player is winning, then we are avoiding +1. When a player is losing that particular match, we are avoiding -1. Like if you go for chess, we played chess, right? If you see the branching factor, like at 3 case, I told you branching factor is 2, right? So in chess case, if you see the average branching factor is 35. Not only branching factor is important, but also depth is important. And if you see the game often require 50 moves by each player. So I can say 35 is the branching factor, 50 moves by one player, and another 50 moves by another player. So this much nodes you have to explore, which is equal to 10 to the power 154. And you know 10 to the power 154 means 1 followed by 154 number of zeros. It is a very big one. It is very difficult to keep these many nodes while you perform a particular search. So one of the method is that if you sure that part of the search strategy you can ignore, right? By applying some kind of knowledge or some kind of thing, if you can do, that is called the process of pruning. So what pruning is doing? Pruning is ignoring the person. Pruning is ignoring the person, ignoring some of the person. Like if I see a 4 square, if a vehicle is moving from this side, now you have a 3 path, right? But I'll tell you, if you move this path, you will never reach to your destination. So this is not coming in your search. You have to only choose whether to go forward or to move right. What I'm doing basically the process of pruning. Now, if you go for min-max, okay, minimax, then there are two players. One is called as max, another is called as min. So generally, max takes the first move, okay, or min takes the first move. The next move is taken by the alternate player, and this process goes until unless the game is over. So see this example. One of the popular example here you can see that is called as backgammon game, where you can give the values from plus 192 to minus 192. These are nothing but the payoffs. If you win this match, you will get +1. If you lose, then -1. If the match is drawn between two different players, then we call the payoff value is 0. So see this example. It is an example of tic-tac-toe, which we usually play. In tic-tac-toe, suppose max symbol is X, min symbol is 0. So max, if it initiates first, it can put cross in any position. And you know there are 9 different positions are there, right? So if you see the number of terminal nodes here, because 9 different possibilities is there. If you calculate 9 factorial, it is nothing but 3,62,880 terminal nodes are there, which is very high. But if you go to the next step, suppose, for example, one player has put here a cross mark. Now you have only eight different cells to put your value. Suppose I'm putting here 0. Then again you have a 7 possibility with your opponent. So the way you will move from the root node towards the leaf node, you will find the number of possibilities decreasing. Initial level, when you do a particular search, it is very difficult to know that how many nodes are there, where to go, but gradually you will see the number of possibilities are decreasing. Like here you can see 3, 12, 8 are 3 different values. Then if you go for this minimax, if you choose min, the minimum value is 3. 2, 4, 6, the minimum value is 2. 14, 5, 2, the minimum value is 2. But once this min has taken this move, then the next opponent player, that is max. Max has to play that one. So what max will do? Max will take the maximum value of these 3, which is 3. Min takes the minimum value, max takes the maximum value. Like that, they alternate each other to play this particular game. Okay, and these are the different complexities, and you can see whether they are optimal or complete or not. In this case, it is optimal. Minimax is optimal. You can go through it. Okay, now we go for a multiplayer game. Here we are not playing with the 2 players. We are playing with more than 2 players. Like here you can see there are 3 players, A, B, and C. Like here you can see in the bottom, there are 3 values, right? One represents A, another represents B, another represents C. Right? Now, if I take a decision here, okay, if I take a decision here, like 1, 2, 3 and 4, 2, 3. So the player take decision is C. So if you look into the C value of these 2 tuple, then you will find 6 is greater than 3. So C is going to choose 1 to 6 instead of 4 to 3. Here if you see the third position, it is 6, 1, 2. So last value is 2. That is nothing but the C value. Here it is the value 1 is the C value. So if I choose, then obviously 6, 1, 2 is going to come. But here it is 1 and it is 2. So obviously 2 is better. So 1, 5, 2 will come. In the next page, instead of C, I am looking into the B values. Like here B value is 2 and 1. So obviously it will come. Here the B value is 5 and 4. Then obviously B value will come. 5 will come. Right? In the next step, this particular step you will take based upon the value of A. In this way, you have to alternate A, B, C, or C, B, A, right? And perform the multiplayer game. In the last one, like if you consider a particular game where there are 3 players, A, B, C, but A, B players are very weak, but C is a strong player. So what you can do here, the optimal solution says that first A and B has to make an alliance. They need to cooperate each other. and they have to attack C. Because individually, if they do A with C or B with C, then it is very difficult to win the game. Suppose by combining A and B, they can destroy C. Okay, they can destroy C, but individually they can do. Once it is done, they have to start their selfish behavior. What is selfish behavior? Now they will break their alliance or agreement and they will attack each other. Because they know the strong player is now not in picture. In order to win the game, AB has to break the alliance and they can fight each other to win that particular game. Okay, so this is all about different sort strategies and different games in the artificial intelligence. If you are interested, you can go through this book. Thank you, everyone. If you have any questions, you can ask. Is there any question? Yeah, if there is no question, thank you, everyone. We'll start the next session at 5:05. Thank you, everyone, for patiently listening.
So good evening, all of you. Uh, Director sir has been joined. Good morning, sir. Good evening, sir. Welcome, sir.
Yeah, good evening, good evening.
1 second, sir. Sanjay, sir, are you there?
Yes, yes.
Okay, Sanjay, sir, let me introduce director, sir, so that we can start the session. So this session will be very
You can start
interactive.
the session.
Yeah, yes, sir. So, Dr. Koteja sir is a professor of computer science and engineering and hold the following positions: head of the Symbiosis Center of Applied AI, SCAI, Dean Faculty of Engineering, Symbiosis International University, Director of Symbiosis Institute of Technology, TEDx Speaker 2015, and author of Introduction to Critical Thinking. He gained his PhD degree from the Indian Institute of Technology, Bombay, India, and is a recipient of faculty mobility grant from the European Union, a LEAP, Leadership for Academicians program, grant from MHRD Government of India in collaboration with IIT Kharagpur and University of Cambridge, UK, in November 2019 to January 2020. DO India Professor Fellowship under Asia European Meeting ASEM DO with Brunel University UK 2020. Two research grants with inner 1.66 crore under promotion of academic and research collaboration SPAS scheme by MHRD Government of India in collaboration with Arizona State University US and University of Queensland Australia. Dr. Koteja was invited and received sponsorship from the Embassy of the United States of America to participate in the US-India Higher Education Collaboration Workshop for establishing international partnership for research and academic collaborations with India and USA. So, welcome, sir.
Thank you. Yeah, thank you very much. So should I start? Is it?
Yeah, yes, sir. Please, sir.
Yes. Okay. So the participants are from where? They are from various parts of the country enrolled for this FDP, right?
Yes, sir.
Yeah, yeah. Okay. So let me share my screen straight away. Okay. Can you see my screen full?
Yes, sir. Screen is visible, sir.
Underfitting and overfitting is written, right?
Sir, it is not. Screen is visible presenting, but PPT is not visible, sir.
Oh, is it? Okay. Okay. Now
Yes, sir. It is visible, sir.
underfitting and overfitting is visible, right?
Yes, sir. Yes, sir.
Okay. So first of all, good afternoon, everyone, and thank you for giving me this opportunity to share my views on a very important topic of machine learning, which any of the machine learning practitioner, or even a learner, even a student who is learning even a first course in machine learning will encounter this, and one has to know how to address this. I would not say it's a problem, but it's an mechanism which guarantees the good learning of a particular model. So there are two terms, which is the topic given to me. One is called underfitting and second is called overfitting. So obviously both of them are not good as far as uh, machine learning model is concerned. We need to have a balance, which we need to have in fact proper fitting, for example, of a particular model. In analogically, even before I start, of course, I need to give some background before I explain this in more detail. Analogically, underfitting happens, let's say, because several of you are teacher or maybe all of you are teachers. When in the classroom, you teach something, and they and you go very very slow. I'll just give analogy and then I'll try to ask you that which is underfitting and overfitting. One way of teaching is go very very slow in the class, and then students will learn, but there is some negative factor here as well. If you go very slow and if you continuously repeat something in the classroom. Second way of teaching is go very very fast, maybe finish 100 slides in 1 hour of your class. Both of them are not good, right? So one is related to analogically underfitting and one is overfitting, right? I will not tell you right now which is underfitting and overfitting. Automatically you will understand by the lecture progresses. So both of them are not good, and you need to have a balance, and that's what the art of a teacher comes into in a role, that one has to be a very good teacher, and very good teacher means he or she will balance both of the things. He cannot go very slow because there will be some fast learners in the class which will get bored. Time requirement will be more, and he cannot go very very fast as well because students won't understand. So it has to be a balance. So likewise, we are teaching to a student by a teacher is teaching to a student. So in machine learning, we need to train a computer by a human being. So same analogy applies. You cannot teach very fast, you cannot teach very slow. Both have their advantages and disadvantages, and finally you need to have a balance. And that's what the terms have come from, same analogy. Before I start, as I mentioned, my second half of the talk will be on underfitting and overfitting, because there is a lot of prerequisites one has to understand. Because underfitting and overfitting, I can put only one slide and I can go on telling that is last 1 hour. But first 1 hour is to have a basic background, why it is occurring, where it is occurring, how it is occurring. So basically, I know that all of you are already undergoing this course, and that's what the difference between these three terminologies. One is supervised learning, second is unsupervised, and third is reinforcement learning. So this phenomena, which is underfitting or overfitting, can happen in majority of the supervised learning cases. It can also happen in reinforcement learning as well, right? But today's talk is focused on supervised learning and underfitting and overfitting under that supervised learning. And this picture clearly explains what is supervised learning. A mom is helping a boy to learn, that is supervised. After that, or even without mom, a boy can read after getting some expertise itself or himself or herself, and that is unsupervised learning. And reinforcement learning is a very very interesting phenomena whereby you learn by doing. You see, nobody can read a book and learn how to walk. So in this picture, a mom, every one of us must have undergone this training by our mom or dad, where we have been taught how to walk or how to swim. All these cases are a classical example of reinforcement learning. Now, if I tell you what is supervised learning, in supervised learning, there are two major applications, in fact. One is classification and one is regression. So the basic difference between both of them, the classification and regression, is here in the picture, which tells that If the student class, you need to find out exam result, for example, pass or a fail. So two different classes. It may be multiple classes as well. For simplicity, I put only two different classes here, pass or fail. However, in regression, there's a variable will be continuous variable. So if you want to predict some percentage of a particular student, that how much marks he will get. If you want to predict tomorrow's weather, for example, if you want to predict maybe or forecast, or maybe you want to predict tomorrow's stock market. So this is all regression kind of problem. So you should know the difference. In both the cases, both of them are under supervised learning, but there are two different applications. Because after some time, I'll be telling you that the underfitting and overfitting is a problem in both the cases, in case of classification as well as in case of regression. It is mandatory to eliminate that particular problem. Otherwise, your machine learning model fails immediately. So as I mentioned, the regression is an outcome of a numerical variable or a continuous valued output, and classification is a category. And as I mentioned, it can be multiple classes as well in reality. This is the simplest example, and this will be also recapped again while teaching you, while discussing underfitting and overfitting, which is, you see, you have been given different data points. The cross marks, red cross marks are my different data points, whereby on the x-axis, I have a size, maybe size of a house. Yeah, it's an housing price prediction, so size of a house. And on y-axis, this is the cost of the house. And based on the selling in a particular area, in a particular country, maybe, these cross marks, red cross marks are given to you. So these are the actual data points which are given, that for 500 square feet, maybe 100 US dollar was the price. That was a selling price. Likewise, 4 plus 4, so 10, 11 points are given to you. Now somebody asks you that, okay, I want to buy a house, maybe which is, let's say 2350 square feet, right? And the data points is not available, for example. Then what is the predicted price? So this is a regression problem, or it's a prediction problem, right? Where some new data point or new variable of an x-axis is given to you, and you need to find out y-axis. So this is a simple problem which you must have solved even in mathematics without machine learning, right? But in machine learning, what is done is machine learns all these data point and find out a smooth curve. See, there are two curves which are drawn here. One is a blue curve and one is a pink curve. So which is better? Seems blue curve is better, right? So ultimately, ideal machine learning algorithm should find out the best possible curve, so that for a new data point, a new x-axis data point, it will find out the best value of y, which will be actual value of y in future as well, right? So that's a prediction problem. And here, if you can, if you've done this in your even undergraduate studies, you know that you can also have a, one particular curve which passes through all the red points in a zigzag fashion. If you do that, it's an ideal curve, ideally, where the error is 0, but your prediction power will be very much limited, because if it is memorizing so many points which are already given, the prediction power is less. So it is same as telling that if the person memorizes the entire book of physics, for example, he or she will not be able to generalize something which is out of the book, or which is out of the book but related to whatever is in the book, will not be able to answer. This is a memory test, right? So machine learning algorithm should not memorize, it should generalize. And for having a good generalizable ability, one has to balance between underfitting and overfitting. So ultimately, we need to find out the best smooth curve which will balance both underfitting and overfitting. That's the goal. And this similar case can happen in case of classification as well, whereby here on x-axis there is a tumor size, and on y-axis you are just having two classes, either is malignant or not. So tumor is good or bad, right, in simple words. So you can draw one particular line, and below the line there is one class, and above the line there is a second class. And of course, we are into AI or machine learning, and so don't expect that there is 100% accuracy. In anyone tells you that my algorithm in AI or machine learning is giving me 100% accuracy, it means the algorithm is not working in most of the cases. The algorithm is memorizing the things, and that's not a goal of machine learning, because memory is infinite in computer on your hard disk. So memorizing is not a learning. That is to be understood always. So here, if you see the boundary line, on the one side of the boundary there is a one class. So it means that if the tumor size is less than some particular unit, and age is also below some particular unit, then it is not problematic. Or otherwise, on the other side it falls, then it is a problematic tumor, right? So this is one of the example of classification. And here also, underfitting or overfitting will happen if your line is not smooth. You can draw a line here as well, a curve rather, where on one side it's only crosses and a second side is only circles. It is always possible to draw, but it will be too much stringent line, and that is as good as memorizing all the points. Ideally, machine learning algorithm should give a smooth line like this, and some of the points which are misclassified. For example, in case of this side, this is misclassified, or here this is misclassified. That is considered as a noise, and it should be eliminated. Otherwise, somebody can go on drawing a line which covers this point on this side like this, right? But that's a memory, and that's what it is overfitting. Ideally, should be eliminated. So if you know the philosophy of classification, this is the way the algorithm is trained. What is done is all these examples, training examples, are given to the algorithm, like text data, it may be image, it may be documents. And then from these documents, the features are extracted. If it is not deep learning, if it is deep learning, this phase is also eliminated. But I'm talking right now in terms of machine learning, whereby the features are extracted. Features, I mean, for example, if you give an image of a motorcycle, okay, then two wheels, two circles are one of the features. If you give an example of image of a car here, okay, on this side, sorry, yeah, here, then maybe four wheels is one of the feature, and maybe a car body shape is second feature. Likewise, there are n number of features which you need to find out, handcrafted using some mathematics, and you need to give it to the algorithm, machine learning algorithm. Once you give that, for example, if you give an image of a car, find out features of car, maybe 10, 20, 30 or 100 features. More are the features, of course, ideally the algorithm will perform better. But soon you will realize that some of the unimportant features, if you find out, algorithm will be in trouble as well. And that also will cause underfitting and overfitting. And labels are my inputs, because I'm into supervised machine learning where I know the labels. It means if I'm giving an input image as car, and if my features are maybe 20 different features of a car, my label is car. Then I give an example of this motorcycle or a bike rather, and my features will be different for bikes, and the label will be again different, which is bike. Likewise, I go on training like we used to do when we were in schools, like 2 or 3 or 4. Once we learn first time, or ABCD up to Z, we learn for the first time. We've been given several times that particular image in front of us. Several times we override that particular image so that our brain learns. So similarly, we need to train the machine learning algorithm. And once it is learned completely, or in given number of classes, right now I give an example of 2 different classes only, maybe a bike and a car. After that, the algorithm is ready after few iterations of this kind. It will not learn by just one example. We never learned as a child by just one example, right? So a lot of examples are required, and then machine learning algorithm is ready. It's learned. But how to test it is ready? There are methods, and the methods should guarantee that there is no underfitting and there is no overfitting. Again here. So now, once the machine learning algorithm is ready without any underfitting and overfitting, you can give a new image of a particular car, a new kind of car maybe, right? It may not be the same picture. If it is same picture, it's a memory. So you are ideally not supposed to give a same picture here, same image, and or maybe same text if it is a text document, and then find out the same way features which you have done here, give to a model, and model can tell this is a car or this is a bike automatically for a new image. And that is what supervised machine learning does. It's very, very simple to understand if you do analogy of how you learned as a childhood. So ultimately what is done in nutshell in supervised learning is you have been given a label data, and you've been given a model, which is a random model initially, and then you fit a model. Fit a model means this particular iteration I was telling you, did these all kinds of iterations. And of course, while doing iteration, there are a large number of algorithms. One of the algorithm is, let's say, backpropagation algorithm if you're using neural network as a machine learning algorithm, right? If you're using other algorithms like support vector machine, you're using, maybe random forest, maybe decision tree, there are a large number of algorithms, and for that you need to use different learning methods. But ultimately within the learning, there is a base algorithm which works, and that is called gradient descent. So I'll give some overview of that as well. So once you are into supervised machine learning, your model, which is randomly initialized, will be fitted to a model which is ready and learned. This is a model which is fully learned what the label data says. And then what you do is you have been given a new data, which is you're not having a label, which you've done here, a new image of a car, give it to a same model which you learned, and it will predict the labels. And that's what is supervised machine learning, right? But within that, what is the type of model you are supposed to use? What is the kind of machine learning algorithm to be used? How to make sure that accuracy is very good? How to make sure that it is not overfitting? How to make sure that it is not underfitting? Which are the things you have to consider? Because there are meta algorithms or meta models as well. So all these things is a part of entire course, which is called supervised machine learning. In case of regression, that previous case was in case of classification, but in case of regression also need to do very similar, but on a continuous variable, which you need to predict. There are no classes, 1 or 0, or I give an example of 2 classes like bike and a car. But here in case of regression, it is going to be a variable, a continuous variable. So maybe you have been given a movie data with the revenue that, okay, this movie produced this particular revenue. You fit a model via some algorithm, then a new movie comes, you can predict that, okay, this particular movie will generate this much revenue, right? Because there is yesterday there was a new movie which is released, is generating huge revenue, that's in news, and that may have been predicted based on this kind of algorithm. And if you can predict, and you can prove, and if you're the person trusts this particular model, then you can have a lot of more business, because you can convince the theater person, maybe a PVR person, that okay, this model is giving this much revenue prediction. It means you're going to be a super hit movie, and that's what you can have it. You can picturize that in your theater, right? So this is a very, very simple looking thing, but there were huge commercial values as well, even though it's the simplest possible algorithm, right? So that's regression. So I'll tell you how this training is done, and from there we switch to our main topic, because without these basics it's very, very difficult to explain the same. So basically, yeah, this is some animation, but basically the framework is like you need to have a training data. You need to find out the best for this particular function, and ultimately find out the best possible function, means the best possible model which will do this classification, right? So let's not go in too much detail here, and that's the supervised learning. I'm sure you understood, so let me skip some of the things. What I was trying to tell here is there may be large number of functions which classifies this particular picture as a cat, but you need to find out the best out of it, the optimal one. That's what there is an F star. So this is a little bit of mathematics to explain the mathematics rather. But let's skip this. And whatever we have done is a training thing, and there's something called testing as well to be done. So this particular picture tells that if you want to classify monkey, cat, or dog. These are the labels given. You find out a best possible F star. It means you find out the best possible model. But then finally you test on this particular image, which has never been told to the model. You see, this particular cat has been used for particular training, but not this. And for us, for a human being, it's very easy if it is tilted like this, and you can find out this is cat. But a machine learning algorithm will take a lot of time in that. Okay, so for machine learning algorithm can also should rather tell this is a cat, right? And that's a call. That's it's successful, then it is test is successful. But there's one more terminology here in general, which is validation, which is very soon I will tell. So these are some of the steps of machine learning algorithm. But let me put it all these things in very simple way, which is a neural network. And if you know something about neural network, then it's easier to understand how the training is done and how overfitting, underfitting works. So I'm not sure that neural network has been taught, but let me just recap very fast. In neural networks case, you have, let's say, a neuron. This is a neuron in between this one. And you give inputs. All the inputs, maybe they are the features, K features, which you extracted from a particular image or particular text. And these weights are the random weights initially, but finally the weights are the learning parameter. In the sense, finally, once your algorithm converges, you need to store weights. For example, you learn something, it means, your brain is trained, and brain is trained means your W's are final. That W's you have to use for new particular feature, and it will classify the same variable as an output. So in case of neural network, what is done is all the features with random weights are given to the neuron. This is one of the neuron, and there may be large number of neurons. It will give an entire network. Like people are telling that in our brain, there will be 10⁶ to 10⁻10 neurons. This is B, which is also an input. It's very, very important bias parameter. I'll not tell you the detail about that right now, but always with one neuron, you need to have one free variable without the features, which is bias, which is mandatory because of nonlinear separability. And this is output Z. The output Z is passed through one function, always a nonlinear function, general, and that is called, this is a sigmoidal function, or it's called an activation function in general, and you produce the output A. Why this has been modeled like this? Because the researchers have found that in our brain, every neuron does this. Every neuron out of 10⁶ to 10⁻10 neurons have this kind of structure where some signals are given, something happens to the signal in between, some multiplier factor between 0 to 1 is multiplied by every signal. The signals are collected, get summed up, okay, with some bias, and the signals get operated in a nonlinear function by a center of a neuron, and then the output is produced. And this kind of, there are huge number of neurons and they are interconnected. So this is a neuron. These are the weights. This is bias. This I told as an activation function. And now generally bias is fixed. You can fix any number, automatically the weights of the bias will be adjusted. So for example, now the input are my features, but features are in numbers right now, simplest possible example I'm giving. Then what will be done? It will be summed up, a weighted sum. And then this particular function, which is an activation function, there are large number of options here. The one of the option and a very popular function is sigmoid function, which is varying between 1 to 0. It may be 1 to -1 as well. You just add some parameter. So if you give Z is 4 here, in fact, and that's what you can get the value of sigma Z, which is an output. So an output will be always between 0 to 1, right? So there are a lot of advantages of using this sigmoidal function, and anyway, it's mandatory to have a ideally nonlinear activation function, because that kind of things happens in our brain as well. So, and after this processing is done, the output is produced from the neural network. And let's say it's 0.98. And analogically, it is having so many such neurons, because you see this is our brain structure. If you decode that a small portion, this is one neuron, this is second neuron, the signals are going from one neuron to another neuron, from this neuron to maybe multiple neurons. So likewise, they are fully interconnected. I'm not saying there are fully densed connection. There are some connections, some of them are not. Some of them dies off once we do aging, because our sometimes memory lost, not completely, but and some of the things is better to forget. We should have an ability to forget some of the things in life. So all these things the researchers have found, and ideally all the researchers are trying to do exactly same on this network, so that our brain is the most powerful learning element right now, and that's what this network also becomes the most powerful learner. So that's what a neural network does. You see all the sigmoidal function output which are produced here. This one neuron is this one, this neuron maybe this one, right? And they are connected with each other. So that's an entire architecture and of the neural network. Of course, you may study in too much detail about neural network, but today I'm just setting the context for something else. So different connections here lead to different network structures, because this structure which I have shown is one of the infinitely many structures. There can be any different structure for learning a particular task, right? It's not generally in a neural network, the limitation is the neural network is designed for a particular task, for image processing, and for example image processing of a particular class of images, unlike human brain, which is multitasker and do hundreds and thousands of different things together. So that day has still not come where it can do everything. And particularly the supercomputers do so many things, but still the common sense and so many other things are still yet to be achieved. Even ChatGPT, which has come now, doing so many things from the previous experiences, but still there are foolish mistakes as well. Obviously, a lot of things to because it does a lot of sophistication, and there are a lot of issues. I don't know about ChatGPT or not. If you ask ChatGPT to produce a research paper on some particular topic, it does that. But it's in generative mode, and that's what it also generates the references below the paper, which is a wrong phenomena, because the references must be there already existence one. You cannot generate a new reference. Right, and there are several such cases where it has been quite successful, and there are some cases where still there are challenges. Of course, it's a very, very good thing, but there are challenges ahead as well. So here, as I was telling, that weights, which I was showing in the last figure, they are and bias, they are the learning parameter, which we need to learn by training the neural network. And in combination, weights and biases are called theta. Theta is the parameter which is to be learned. So there will be huge number of theta. Every arrow will have a weight here. And if you combine all of them, there will be, let's say, 1 million or 10 million or 1 billion parameter for a particular network. They are still less compared to deep learning network, which is having even more than that. So this is one of the example of a network which is fully connected, which we call as a feed forward network. And why it is feed forward? Because here you give two inputs, maybe two features, for example, maybe two wheels and maybe a handle of a bike. So that are the two features, and then these are initially random weights. And once you give a feature, it will do this multiplication task, it will do this nonlinear and produces this 4 here, rather produces 0.98 as an output here, and produces 0.12 as an output here after operating on sigmoidal function. Right? This is just a sum total. -2 is nothing but a weighted sum total. So likewise, it propagates, and then finally the outputs are produced. Right. So, and then suppose your suppose your input changes, then output will also change accordingly. Right. So this is a feed forward. I'll tell you why I'm telling this. So the input changes, the calculations of the output. I'll pass it on the slides as well, so no need to right now calculate them, but it produces the output, some particular outputs, and these outputs, because now we are into supervised learning, we need to compare with expected outputs. We know always once we give this as an input that this is a feature of a bike or this is a feature of a car, and if it is a feature of a bike, what should be the expected output? If it is a feature of a car, what is the expected output? That is known. So you compare this output of this feed-forward neural network with the expected one. It will not match initially. So whatever is the difference, that using that difference, you need to change all these parameters. 3, this -1, all these parameters, all the weights and biases, you are supposed to change such a way that whatever is the expected output, this output will be matched with that. And that training is using back propagation algorithm, and internally it uses gradient descent algorithm. So whatever I told, that can be written in a matrix form, because once you represent in a matrix form, it's easy to manipulate in the programming languages. So you can write in matrix form as well. But the basic philosophy I wanted you to understand is that if you put some features here, you produce some output, and you know the expected output, which of course in subsequent slides I will tell, and then you measure the difference and propagate that difference back all the way to the network and change most, if not all, parameters of the network. Whatever the numbers you are seeing, change most of them or all of them in a systematic way using some particular standard algorithm in such a way that this output and expected output and this output and its expected output are very close to each other. They may not be exactly same. If there's an exact same, either it's a toy problem where you need not to have a machine learning algorithm, or there is an overfitting. Okay, so if it is exactly same, you need to go back and check that there is something wrong here. It is same as telling that if in a language subject in 10+2, if somebody gets 100 out of 100 in Marathi or Gujarati or any other language, we feel little doubt that okay, it's I don't think there'll be some error here, right? So it's very similar to that. So this is a fully connected layer which I have shown. I have redrawn here. And some of the terminologies are, this is called input layer, this is output layer, and these are all in between hidden layers. So number of layers can be many, but there are some guidelines in the literature of selecting number of layers. And final layer, this final layer, before I tell you how loss is created or calculated, I'll tell you about the final layer, how it has been calculated. Because these layers are giving input to this other neurons, but these layers are final output which are to be matched with the expected output. So there is some difference in this particular layer, and this particular layer is called generally a softmax layer, whereby whatever I have drawn is an ordinary layer whereby your input is Z operated on sigmoidal function and it produces Y. So it's the same. These are all Z and it produces Y. But in case of softmax layer, there is some calculation is done. Just see this calculation, not that difficult. If Z1 is given as an input, my Y1 will be like this. It's nothing but e raised to Z1 divided by sum total of all. It's just a scaling. This is just a scaling. Okay. And it is e raised to Z1, so that my output in this case will be always between 0 to 1. And it means it is as good as it is a probability, right? Because in case of classification also, once you will never get Z1. Suppose you are giving 3 classes. One is for again bike, this is car, and maybe this is some other vehicle, let's say airplane. You will never get, suppose if you input car as an image, ideally Z1 should be 1. You will not get directly exactly 1. You will get, let's say 0.9. It means what, 90% chance that it is a car. Here it may be 0.5. So it means 5% chance is, same image which is actually car is actually a bike, right? So this will not be always 100%. So we'll give a probability, but of course, highest probability is your class. Right. In some cases where, if it is a leopard and a panther, at times it, or maybe a cat of this different category, wild cat, it's going to be difficult by an algorithm to find out and differentiate. Then this kind of probabilities will be very useful, where it tells 55% chance it is a panther and 45% chance it is a leopard maybe, right? So if there are similar classes are there, then also because of probability you'll be able to tell which class it belongs to. And you cannot give 100% guarantee. Again, you are into artificial intelligence, you have to tell 55% chance of this particular thing, and you need to increase that chance by training algorithms, doing lot many other juggleries, adding more data, adding balanced data, changing the algorithm, and so many other things are there in machine learning, which you need to try and experiment to increase from that 55% to maybe 75% to 85% to maybe 95% for two similar looking classes. And that's an actual challenge. And that's the where actual machine learning algorithms are used. Otherwise, it's very pretty simple. So this is the last layer always of a neural network. That's what I'm trying to tell, and which gives us the probability in case of if you are doing a classification problem. So some calculations I have given here. The input is 3, 1, and -3. So you calculate e raised to 3 is 20, maybe e raised to 1 is 2.7, e raised to -3 is maybe 0.05, and then you do the weighted average and you get this, right? So this is finally a probability. It will always add up to 1. Right, so that's an advantage of using the softmax layer, which gives you the probability at the output case. Otherwise, also you can find out this 3 is the highest value, so this is the class, right? That is the class, but there are a lot of advantages of making and converting into probability. So to summarize this, I have a picture of image of 2, and which is a 16 cross 16 pixel image, so 256 pixel. So I need to have 256 input to my neural network, 1 or 0. If there is a ink, that is 1. If there is no ink, that is 0. I can have entire network in between, sorry, entire network in between here, which is not drawn, and this is my output of the network. What is that output? Softmax. So output sum total is 1, 0.1 plus 0.7 plus 0.2. My expected one, because it is 2, this actually should be 1. This here output should be 1, here output should be 0, here everything should be 0. Right, because my this particular picture corresponds to 2, the second output should be highest, remaining ideally to be 0. But it is not highest. It is highest, but it is not closer to maybe 1. So there's more training is required. Right. Initially, it will not be 1.7. Initially, it will be maybe 0.2 only, because initially the network is random. Right. And that's what there'll be an error, because 0.2 is the output, but you want is S to be 1 because it is digit number 2. Right. So you reiterate and then finally do this. Finally come to a stage where your output and expected outputs are more or less same, or the difference between your output and an expected output is less than epsilon. And epsilon is our design parameter, which based on the criticality of the application, you need to find out. So we need a machine learning algorithm which will do this. Your input is 256 dimensional vector because they are the number of bits, your rather pixels. Your machine learning algorithm is initially random. Your output 10 dimensional vector because possibly you are classifying 0 to 9. Handwriting, handwritten digit recognition is the problem. So neural network will be trained, and this is the entire network which is need to be trained. So I think now you got the idea that what I'm trying to do, that trying to change my parameters so that my output and expected output matches. Right, and you need to find out, lot of images to train the network. Like this is 5 and this is 0. So all these images, and this is one and this is also one. So you need to have a lot of variations in your images while training. If you only train with this, then it will not work if you test with this, right? So all complications also needs to be trained. So twisting while training is also important. So I'll just keep some of the things because now I think you have got the idea of what we are doing. The terminology which you should know one more here is loss. The loss function is what? A difference between this vector, which is actual output, and difference and this vector, which is my expected output or a target output. And target is always given in case of supervised learning. And difference between these two vector is a loss. Now, there are large number of parameters, large number of methods by which the loss is created. One way is, let's say, this minus this, y2 minus this y2 dash maybe, okay, or then maybe root mean square error, or maybe some other loss as well, right? So cross entropy loss as well. Generally, cross entropy loss is very popular in case of classification. So I'm not going to explain that today, but that's a very, very important loss, which is called cross entropy loss. It depends on the it is derived based on the entropy of a particular function, right? So this loss is calculated for a particular problem, and the loss is to be minimized finally by training the algorithm. I'll give you time to ask some questions after maybe 5 minutes. So yeah, let me give you some bigger picture here, where these are all training data, and I'm giving to neural network, finding the loss. For example, this is the entire neural network. This NN is all 256 parameter, X1 is 256 dimension, 5 is given. Output is some particular value, and this y hat should be such that this is 5. This y hat 2 should be such that it is 0, but it will not be. So there will be difference between these two terms initially, y1 and y1 hat. That is called loss L1. Similarly, there will be a second time if you put 0, there will be again a loss. If you put 4, if you give 4 as an input to the neural network, again there will be a loss. So likewise, there will be a large number of losses. So you need to sum total of all the losses. And then sum total of all the losses must be as small as possible. And this is not going to happen in one iteration. For example, you give 5 and try to minimize this loss. Suppose you minimize to a very low value, epsilon, then you give 0 to the same network. The network is same. Okay, and you change again the parameter to make network learn 0, it will disturb here as well. So 5 loss will increase while you train for 0. So you need to do lot of such iteration. Plus the beauty of, or rather a problem is of the network is, if you train in this sequence, it will memorize the sequence. So you should not memorize the sequence. Sequence is not important here. So you have to shuffle the sequence as well, right? So all these things are to be, understood while training the network. So I'll skip some of the things now, and coming back to gradient descent, and then our topic, which is depend on this. And after gradient descent, I'll give you some break for questions. If you have any questions, we can do right now also. I don't have any problem. I heard some voice. So any questions by now or? Okay. So the network, while changing the parameter W1 and all W's and all B's, it does and follows this kind of curve, a loss curve. So whatever was the sum total of loss, I have plotted here in only 2 dimension. It may be n dimension, so it can't be plotted so easily. Of course, there are methods of SNE plot and several which plots in a very user-friendly way. But this particular loss, what I'm supposed to do, if the loss is higher, I'm supposed to go down to this particular point. But that's a local minima, because ideally the loss should be here. But you don't know this, right? If you know that, you will not do any training, in fact. And that's what, once you stuck here, there are large number of methods which will make you to this point. But if you are in this point, it does not mean that in future there is no point which is lower than that. So finding that bare minimum point is a global minima problem, and it's a very difficult problem which machine learning algorithm needs to address, right? So ultimately what I'm trying to tell is the minimization of the loss follows this kind of gradient descent. And for that it's difficult because you need to compute a gradient, and if it is, yeah, this is a gradient descent algorithm which I'm trying to explain, where you have to follow the negative of the gradient descent. So if it is a negative slope right now, you take a positive step, and if you are negative gradient, if you are positive slope, then take a negative step. So likewise, you need to change the values of W's, which let us not go in detail. Maybe there is some other talk on that. And then stuck at local minima where the slope is 0, there needs to be done some juggleries. There can be a saddle point where also the slope is 0, need to do some other juggleries. And then maybe plateau where also the slope is flat, means 0, then also you need almost 0. You need to do some other mechanisms, starting from simulated annealing to so many other momentum methods, and large number of optimization algorithm comes into play to just get that particular local to global minima. Maybe there is an entire course on that, right? And story doesn't end there. If there is a function which is not this differentiable and not like this, you need to go for maybe evolutionary algorithms and an entire course on evolutionary computation as well, only based on finding this global minima, right? This curve can produce a couple of courses, and then only you can solve this particular problem. So and this all can be used for spam email and so many things, but let us go to our topic of data set and underfitting, overfitting. Now you will be able to understand and realize why I'm doing this. In data set, which we are using for training, there are three terminologies to be known. One is called training set, one is called validation set, and third is called test set. Now let me start with an analogy here. Training is nothing but a classroom teaching. For example, you are teaching to the students in your class, and after, let's say, end of the semester, you take a test in between also, but at the final you take a maybe summative test, and that is same as validation, whereby you judge that, okay, 70% is the result or 80% of the result. And nowadays this OBE is very popular. So as per outcome-based education, this is the attainment of my class for a particular subject. Of course, subject-wise, this is the attainment, and that is exactly the validation is. But do you think that if your attainment is 100%, in future 100% of them will get a very good job or 100% will be successful? May or may not be true, right? And that is what testing is for, something which is totally outside world. So you are judging your own student, that is your validation. I'm just giving analogy, I'm not telling exactly same, but it's quite a good analogy to understand. In your class, whatever you are doing, that's a training, and in between you can get a feedback also of your training. You can take a very small test, and you know that, okay, your training is going very well, the accuracy is very high of your learning teaching, so students are learning well. For example, at the end, you take a test which is a validation test, which you get attainment of a particular course, and then once they study entire program, they go out, they face the challenges in the entire world, and then their performance is tested, and that is a test set. So machine learning algorithm should be able to get successful in all three, because you are training, for example, a machine learning algorithm for image recognition of couple of objects, right? So, and then training is very good. Then validation is also good, and that's what you deploy the model and give it to your customer, that, okay, you see, I have trained, now right now you validate that, okay, you give a new image of a bicycle or new image of a let's say your car, accuracy is fantastic, fine. But then he deploys rather a particular model, and then a new model of a car comes, right? And then your accuracy, test accuracy at that time should not be much lesser than what was there at the validation time. And that's an actual acid test of your model. And that is a difficult challenge. And that's what it will not hamper much. Your accuracy of the test will not hamper much if you have taken care several things like underfitting, overfitting, and of course, not only that, there is something called domain adaptation, but that's out of scope today. So once you have been given a data, whatever amount of data you have, more the data is better the algorithm will perform in general. So whatever the data is given, the first method was that you keep 60% of the data for training to train the model, 20% for validation, and 20% for testing, right? So this was the scenario, but here I'll not tell you much because this is an old one where you are losing the 40% of the data for training, because your own data having 100 samples, your 60 samples only used for training, 20 for validation, and 20 for testing. So it means you are losing 40 for training. So ideally majority of them should be used for training, and that's what there's a novel method. So I'll switch directly to that, which is your data, training data. Within the training data only you create something called validation holdout, and then there is a testing. So now 80% of the data ideally can be used for training, but 60% at a time. I'll tell you next figure how, next slide, and testing is 20%. So it's done like this. Your 100 samples, out of 100 samples, let's say your trained data is now 80%, not 60, and your test is 20%. Test data is never used, never been shown to the algorithm. It is like after deployment, some new data will come. As I mentioned in my analogy, that after you deploy the algorithm, there'll be new data will come. So this kind of data, which are never used for training, that's a different test data you put. Within the trained data, what you do is you have one particular portion of the data that is used for validation. So if I have total data, these are total training data. Let's say out of this 5 means 20% of the data I'm keeping for validation. So what I'll do is first time, this is all trained data, but first time I'll train the algorithm only with this much data, which are in green, and validate using this. So I'll find out the accuracy. Second time, same data, but randomly this particular block I'll select. This is not exactly the sequence 20% examples, but randomly 20% examples out of this total I'll keep out for validation. So remaining data, this, and this, I will train and find out the validation accuracy using this block. And likewise, maybe 5 times, because I'm dividing it to 5 different portions here. It can be 10 as well. And then average out. That is my validation accuracy. So what is the beauty here? That I have not lost that 20% of the data for training as well. You see, in this case, I was losing 20% data because they were never used for training. Here I'm using them for training, but remaining data I'm using for validation. So that's a very, very popular method, which is called N-fold cross validation, which is used in most of the machine learning algorithm. Generally, it is only used, and you can do some difference based on your application, but this is a de facto standard. And then once your training accuracy and validation accuracy are good, you can do testing as well. And testing accuracy also should be very good. But it will not be the case, and that's what you need to do, something called regularization. So what will happen is, once we have data like this, which we started, this was my first slide, when we had some data, blue points are given data. I can fit this curve, or I can fit this curve, or I can fit this curve. So I'm sure immediately you will tell that I think this is a good curve compared to at least these two. May not be the best one, but between among these three, this is the best one. Why? Because here it is too much of juggleries. There is no generalization. So here what you can expect, your training accuracy will be 100%, because training data is fitting 100%. But if what will be my testing accuracy? doubtful because I am not having a smooth curve. So if I want to find out for a new point here, it will be something zigzag. It is not smooth as this, right? And that's what my output test accuracy is going to be really very bad. And that's meaning of high variance. That's called high variance rather. In this case, it's underfitting because my model is very, very simple. Model is straight line, right? So regression model is very, very straight line. Actually, my data points are like this, right? So of course, there is a model which is doing something, but most of the time there is an error in training only, because even if I give a same training data, you see this data is for training data is also having error because this is an error. Because if I give this X, okay, it should give me this as Y. But right now it will give only this as Y. So there's a huge error in predicting Y given X, right? And that's what it's called underfitting, because even in training there is an error. So you cannot do even testing and validation further. So this must be avoided. This must be avoided where even my training data is not proper. This means your classroom teaching is really very bad. They are not understanding in class also. So how they will perform in some different and difficult examination. Here in the class, they memorize everything and that's what they will not perform better. Both the cases is a dangerous thing. So you need to have a good balance between both, and you need to have a better curve. And that is having, it means low bias and low variance. So in general, I'll not go the bookish definition. Your bias is a training error. It's not exactly, but it is equivalent to training error, and variance is equivalent to your testing error. One is to have a good balance. So I have a slide which tells what is a good balance, but you can only tell that this is a very simple model. So if the model is better, more advanced, then it will not have an underfitting. But this is a too much of an advanced model. This is a multi-dimensional curve is getting fitted. Here is a maybe single 1 or 2 dimension curve is fitted. So it should be a balance between both. Whatever I told can be represented or explained using this figure as well, whereby low bias and low variance means compared to real data, your targeted data is also nearer. So everything is in close vicinity. So this is an ideal model. If model is, underfitting, it means your real data is this, okay, but you are fitting the model here, right? So even training is not good, and overfitting means your training is good on an average. If you take an average, they are closer. The average is 0. They are closer to real data because this is an error, this is an error, but average is 0. But this is because they are predicted data, but they are still away from the real data. It means what? Your testing error is very high and should not be the case. And of course, this is not in a model at all. So both of the things should be avoided: underfitting and overfitting. Again, analogically, this is the case. Here, one can have this curve, so which is a straight line. You see, is y is equal to mx. It's a straight line. Not good. It is underfitting. This is very complicated curve. 4 dimension, so it will pass through all the data points. So it is overfitting. We need this, which will be a smooth curve. May not pass, but very close to all the points. So also, one more learning here is, if model is too simple, it leads to underfitting. If model is too complex, it leads to overfitting. Model needs to be balanced. But we don't know these points, and that's what we don't know which model should be there. If you know that, there is no need of machine learning, right? We don't know this is the equation of this particular curve. If it is so, it means this is the output of a machine learning algorithm actually. So if you know the output, where is the need of training? And this is what we don't know. So what we can do is we can start with this, and we can go on increasing the complexity of the model to this. But you see that now there is a suffering, and that's what you go back and give this particular model as an output. This is one way. Second way is, if you already have this kind of model, very complicated model, you eliminate this x4 and x3 by putting the values of theta 4 and theta 3 in such a way that it will truncate the influence of feature x3 and x4 means the quadratic and x raised to 4 features. So that is also one way, and that is called actually regularization. I'll summarize this. So same is the case in case of classification, that if it is a very complicated function like this, classification will have an overfitting. If it is a very simple, it is going to be underfitting, and this is the required one. So this is the most important slide here, that once you are training the network or in any machine learning algorithm, your training error is big. It means you are underfitting. Easily possible to find out, not so difficult, and that's what you need to change the model. So if you are using, let's say, a simple model like decision tree, which is prone to this, you need to go for, let's say, support vector machine, or maybe a neural network, or maybe a random forest. So you can change the model. But for example, the training error is really good, small, then you go to the next step and you do the validation. I have told you what is validation. So once you are doing validation and a validation error is big, it means there is an overfitting. So you need to do so many different things. If it is overfitting, I'll tell you what. Oh, sorry. Then if validation error is also small, you do the testing, and testing error needs to be ideally small. So it's a good model, but by chance your test error is big. Okay. After your validation was good, you see, these two are in your control, train and validation in general. Right now we are doing testing also in-house, but finally testing will be done actually outside once you deploy. So if testing error is higher after the validation error is small, it means what? The examples on which you are trained, similar distributions are not there for testing. So then it's a bigger problem. Then you have to go for, let's say, domain adaptation is one of the mechanism I know, because recently we published, but there are so many other methods as well. Right, whereby I give a simple example that if you have trained on different kinds of pictures which are very good, but then you train on then you test on actual pictures. For example, you have trained on different computer parts, mouse and screen and desktop. But while testing, somebody gives a photograph of a laptop or a different mouse, which is from Apple, for example, okay, or a wireless keyboard, or maybe Apple keyboard. So they are totally different in size, shape, even though they are keyboards, and even the different lighting conditions, different actual photographs. It's not a curated photograph which is edited, actual photographs, then it is different, right? So in that case, you need to use different methods of machine learning, very advanced ones, including domain adaptation. But our goal is to eliminate both of them. And you know, again, that if training error is higher, underfitting, validation error is higher, it is overfitting. One way is, as I already mentioned, you increase the model complexity. So your y-axis is model complexity. You go on increasing that. So initially, if it is model is very simple, you will be in underfitting zone, like a straight line, if you remember that particular figure. And once you move out from that, what will happen? Your overfitting will be more, right? And that's what you need to stop here. You need to balance. So this particular zone you are supposed to find out, and this particular model complexity you are supposed to find out. So even now, there are very sophisticated algorithms like neural architecture search, NAS, which finds out the model which you are supposed to use for a particular problem. And there is an auto ML which finds out it automatically as well. So there is a lot of advancement. This is a very very basic course. So I'm not going to cover that. So these are the solutions. Few of them intuitively you will understand now, but some of them I'll tell in the next few slides as well. Is if there is an overfitting, you need to simplify the model. We have seen that there were more thetas, theta raised to 4, theta x raised to 4, x raised to 5. You need to simplify the model if it is overfitting. You can simplify the training data as well, right? Sorry, I'm just giving out a mode. So you need to simplify the training data as well. That is also one way of reducing the overfitting. Or you can do regularization, which I will tell now. Cross validation anyway we are doing. Or you can do early stopping of an algorithm. You see, you stop here. You stop this algorithm here. Or build an ensemble. Ensemble means use multiple machine learning algorithms and try to find out balance of all of them, or collect more data, because generally overfitting happens when there is a small amount of data. Let's say medical problem, if you're solving using machine learning, the data is always limited, and that's so there's a huge chance of overfitting, where you'll get training accuracy 100%, but testing may be even less than 60%, right? If it is underfitting, very simple model, so you need to increase the model complexity, you need to increase number of features, right? So feature engineering you should do. If you are doing regularization, in general people do, you need to avoid that. You need to reduce the noise in the data, or into train for longer time. Like if students are not understanding, you repeat the things, right? So some of the intuition you know already. Simplification of the model I have already told, like from this picture, that this is simplified one. Sorry, this one is simplified one. This is very complex, x cube, x4, which is not required, but only x is also not okay. So this is a balanced one. So simplification means penalize this term. Penalizing this term is called regularization. Theta is such a way that theta 3 and theta 4 become tends to 0. It means it will be only this much, which is the ideal condition. One more way I told out of this is collect more training examples. So if the training examples only are this 5, you see the how model is fitting. But if you add more examples, it may be a smooth curve. So that is also one way of avoiding the overfitting. Another way is select the features. So if you select all the features, there are a large number of features, size or bedroom or number of floors or age of a house or age of a person or average income, everything. And if data is less, if the features are really very sorry, I don't know what's happening. If the features are many, but the data size is very less, then it's very huge chances of overfitting. Right? So you need to select only few features which are dominating, and there are methods of selecting the dominating features like principal component analysis or LDA, or so it's based on supervised and unsupervised learning. And then select only few features, and because the data is anyway less, there is no point in having large number of features. So select few dominating features, then overfitting can be avoided. Of course, the downside of that is some of the information you will lose always once you select only some of the features. One more method of eliminating overfitting and underfitting, rather overfitting, is regularize, which I already told that this is my equation, which has been obtained from the data, which is obtained from the data means learned. And this is an output of a neural network learning, right? What you do is, this is overfitting curve. It's not smooth, passing through all the points. Why? Because there is an x3 and x4. You need to eliminate them. What you do is, you make their coefficient very small. How to make it? You do regularization. That's the next slide. If you regularize this, it will be at this curve, which is definitely better than this one, right? So doing that, there are multiple kinds of regularization. I'll skip this to explain the regularization. So one of the regularization method is this, whereby this is your actual prediction of a regression algorithm. This is also a neural network representation. What you do is you add this particular term, right? So ultimately you are adding something to a loss. I cannot go in more detail right now, but what you are doing is, this is actual error, but you are adding something more to error, and that is in terms of W's. If you do that, it is having an effect like this. That much you can understand in such a short time today, that the effect is this x4 and x3 effect in fx will be almost eliminated, and this curve will become better, if not the best one, by adding a term, some term, which is dominated by weights, and weights are the learning parameter in loss. So you are giving more loss to the network. So network will take more time to learn, but it helps in overfitting, elimination of the overfitting. Somebody can do WI, but somebody can do WI square as well, and that's a faster one, or more addition of the loss, and that is L2 regularization. This was L1. Both of them are one of the methods of eliminating overfitting. And always there is a balance. So if third person has found balance of both, you can use both this one and W square. How much? Again, meta parameter, design parameter. You can do 10% this, 90% this, or 20% this, 80% this. So alpha is again a varying parameter. Somebody can do this elastic net regularization. Right. So why I'm telling regularization, let's recap a little bit that because of this, if I want to eliminate overfitting, one of the method is regularization. I told about simplifying model. I told about training data. You can simplify the training data. You can do cross validation. You can do regularization. So now I'll tell about early stopping. So you can do early stopping as well. Oh, I'll skip this. This is not for you. So early. Oh, sorry. One more method. Let me go and tell is. Oh, it's not written here. Okay, but this one of the method is this also, which is dropping out. So this was a neural network which we trained, but if you trunk cut some of the points, just switch it off, some of the network parameter, just switch it off, then also it helps really in avoiding overfitting. Right, it's really very powerful method, which is actually similar to regularization, where we are eliminating effect of some of the parameter. Right, so that's a very easiest way to do competitive and regularization. If you are using neural network, it is applicable. If you are using other methods like SVM and all, you need to go for regularization to avoid overfitting. And the last method is early stopping. Second last method is early stopping, whereby you always measure and plot while you're training the model, your training error and testing error. And once the testing error starts shooting up, it's not going down. That particular point, which is a dotted line here, you stop the training. That's also one of the way. Right? It's not a great way, but sometimes it works. And the last method is ensemble, as I mentioned, whereby you combine several of the algorithms. I'll not go, our time is almost getting over, where there are a large number of ensemble methods. Bagging, boosting, and random forest is one of the classical example of that, where what you do is you try to combine different algorithms and take the advantage of all of them. And that also reduces and balances rather underfitting and overfitting. So I have a lot of slides for that, but not for you today. And it really works very well. So the recap and learning only for last 1.5 hours is how to reduce. What was that? I tried to prove using different methods, making it self-contentive, and overfitting means simplifying the model using regularization by default. That's the easiest way. Doing cross validation, early stopping, ensembling, or collecting more data is always in one way, but it's always the costliest way. Collecting more data is an nightmare at times. If it is a medical application, it takes years and years of time, and it's sometimes impossible even to label the data. And underfitting is very easy to find out because it's just a training error. So you need to increase the complexity of the model. Your number of features are not enough, and that's what your training accuracy is not happening. So it's like same as telling that in the classroom, it's very easy to find out the students are not learning. Simply, once they go out of your institute and they are not performing, you can't do anything. So better to correct everything. And that's what, and it's also easier to find out underfitting, where you need to do, of course, feature engineering. So entire course is there in feature engineering if you are using machine learning, but nowadays deep learning algorithm has eliminated that completely. And if you're doing regularization, don't do if it is underfitting. And if there are a lot of noise in the data, there's a way to find out noise like missing values or inconsistent values, which is a data mining entire course. You can do that as well, or train for longer. It's like remedial classes for the students. So these are the methods for that. So thanks. If there are questions, I can take.